Okay, well, I don't see anyone immediately coming. Let me see.
All right. Just wanted to say hello to everybody and welcome you to the program. It is a small group, but a mighty one. So I hope you guys will have fun and it will be useful. Thank you.
All right, thanks. Okay. All right, so before jumping into kind of what we'll be going over today, unfortunately, good morning. Hello, I'm Kylie Bemis. So this is the Cardinal session of May Institute. So if that's what you're looking for, you're in the right place. And yeah, we'll just be a few people today, not too many, but hopefully that makes it a little bit easier to make it interactive and talk a little bit about it, what we're doing, and allow me to answer any questions that you might have. We can go at whatever pace we want, essentially. So before jumping into what we have for today, I just want to get a quick idea of kind of where everyone is coming from. So I'm Kylie Bemis. I am the main developer for Cardinal, which is our software for analysis of mass spectrometry imaging experiments, which is presumably why you're here. I'm an assistant teaching professor here at Northeastern University in Colorado College. I teach mostly in the Masters for Data Science program. My own background is in statistics from Purdue. My PhD was on developing statistical methods for mass spectrometry imaging, which is how I ended up developing Cardinal as an R package for working with mass spec imaging, because at the time there wasn't really much software when I was working on my PhD for working with mass spec imaging. There was a lot of software for mass spectrometry and proteomics more generally, but nothing really focused on imaging at that time. And so in order to develop methods for it and analyze data, I kind of needed to invent the wheel at that point, so to speak. So that's how I ended up here, and kind of the perspective I'm coming from in terms of analyzing mass spec experiments and mass spec imaging experiments is primarily as a kind of a traditionally trained statistician, who is now in a department of computer science and machine learning and AI and all of that. All right. So since you all have used a little bit of Cardinal, or at least to some extent, or aware of it, I'll also try to mention where things have changed a little bit. So just a brief introduction, which you all know. So mass spec imaging, we have thousands, potentially thousands of mass spectra that we collect across the surface of some kind of sample, and then we can reconstruct images corresponding to different slices of mass to charge ratios from that, which is where the imaging part of this comes from. Uh, some of the challenges of working with mass spec imaging data, kind of a little bit more from a statistical and computational perspective, are of course that we have increasing mass resolutions, more increasing spatial resolutions. So in the time that I've been working with this technology, the mass resolution has gotten significantly better over that time. So a number of the data sets we'll be working with from a decade ago are have much less mass, or never think of if it's greater or lesser resolution, since depending on which kind of numbers we're using, it goes both ways. But not as fine mass resolution as we have today, and even one of the higher resolution experiments we'll look at from a publication today is not that high resolution anymore. So that's one major challenge, which of course leads to larger data sets. So we can have tens of gigabytes up to terabytes of data now. We can have potential for complex experimental designs. So some of the things that we need to consider when designing experiments for mass spec imaging experiments, which is another thing we can potentially talk about later, is how we actually arrange those samples on slides, how we decide which samples to put on certain slides versus other slides, how we decide what order to actually run those, because all of these things are additional sources of variation that we should be trying to account for in how we actually analyze that experiment. So it's good if we can think about all of that at the level of experimental design before we get to the analysis. So those are some of the challenges for mass spec imaging analysis. And as you know, um, uh, we have Cardinal version 3. This is our open source software, statistical software for mass spec imaging experiments, which is what we'll be talking about today. Now, for those of you coming from already working with Cardinal a little bit, well, firstly, we have a new publication, so we have a new citation to use based on our new based on our new publication in Nature Methods. So that's really exciting. This is just one of the figures from that paper showing off a lot of the features that we have in Cardinal now. But what I want to kind of go over briefly with you is some of the kind of new and some of the things that we've been focusing on in the most recent Cardinal update, version 3.6, which was just released last week. So these are some of the main things that we've been thinking about in the latest version, and some things that might have changed a little bit from the way that you might have been used to working with Cardinal up until this point. So one of the things I've been focusing on improving is the data structures themselves. I want to make it easier for people to work with the data. I've been trying to improve our pre-processing functionality a lot because my background was in statistics, so I came at all of this from a statistical methods perspective and did not spend quite as much time on the pre-processing initially because we were relying on other tools and other people for that. But it's important to us to have a full kind of workflow from importing the raw data to the statistical analysis. So we've spent a lot of time over the past year or so improving the pre-processing functionality, which we'll also see. Most recent version also has improved faster statistical methods and more convenient storage of the results. And something that we're currently working on, which we'll talk about this afternoon a little bit, are some of the future directions and future technologies that we'll be working on supporting. Specifically, some of the things that we're thinking about are ion mobility and multimodal experiments. So those are some of our focuses for future developments in the next several years as more data is being collected that fall into kind of these categories. So I won't go into this all of this just now. So I think I'll skip over to let's see. All right. So actually, I think we'll start off by just giving a an overview of kind of the different software that we have and what kind of role they play in our Cardinal ecosystem. So Cardinal is the primary package that we have for analyzing mass spec imaging data. But over the years, it's kind of gotten larger. We've had to add a lot of new features. And so as part of that, I've also worked to break off some of the functionality into a few other R packages. So when you see a few other R packages that we'll be using today, those are some of the other packages that I've broken some of the functionality away from Cardinal to make it a little bit easier to organize and continue to maintain and develop these packages. So one of those is just focusing on import and export of mass spectrometry imaging files. So Cardinal IO is a package specifically for reading and writing of mass spectrometry imaging data files. And I kind of want to start here because in general, when we're analyzing data before we can actually get to that point, one of the first steps we have to do is, of course, to actually import the data. So I want to start off by briefly kind of going over IMZML files and what are the different kinds of IMZML formats, because that is the primary file format that we support in Cardinal. So firstly, who kind of knows what IMZML is or has converted to and used IMZML before? Okay. All right, so just as kind of a review then, IMZML is an open format designed specifically for storing mass spectrometry imaging files. It came about because, well, there are a lot of different vendor-specific proprietary file formats within mass spectrometry and mass spec imaging especially, and the development of open and source and free software, it's kind of difficult to work directly with those proprietary vendor formats, sometimes because we don't even know kind of what their structure actually looks like. Sometimes because we need to use proprietary software in order to actually extract data from those file formats. And so relying on those was just not going to be a reasonable way forward in terms of what kinds of files we can support for open source software. And so fortunately, IMZML has come out as an accepted standard now for representing mass spectrometry imaging files. So IMZML is a file format that consists of two separate data files. Let me make this a little bit bigger. Uh, that. So an IMZML file actually consists of two separate files. There is a .imzml component and a .ibd component. Both of these together is what makes up an IMZML data file. Um, and the reason that we have these two different parts to an IMZML file is that we're separating out the experimental metadata. Come on in. The experimental metadata from the actual spectral data. So we have a separate file for describing the experiment and describing the metadata, and a separate file for the actual mass to charge ratios and the actual intensities that were collected. So the .imzml file itself is stored in what we call XML format. XML is just a common text-based format for, it's technically a markup language, so it's just a common kind of text format for storing any kind of metadata. So let me quickly actually open one up for you to show you. So all of the materials for today, you should have gotten a link. So I'm going to go ahead and look at the IMZML file from this case study real quick. This is a relatively large text file, about 56 megabytes, which is not large in terms of data generally, but if you try to open this in a text editor, make sure your text editor can handle opening it. So this is what, see if I can get some syntax highlighting turned on here. So this is what the XML part of an IMZML file looks like. I want to show this to you just so you have an idea of what it looks like, and in case you need to ever actually find any information from this directly, because it is a human readable format. Not super readable, but it is something that you can actually look at and find some of the different metadata elements that you might need if you do need to end up looking at it directly. So the IMZML part of this format starts off with a description of the file itself. This includes what kind of spectra are in it for mass spec imaging. This is almost always just going to be MS1 spectra. So I should start off by also saying that this IMZML format comes to us via MZML. So if you've worked with traditional mass spectrometry before, you might have used the MZML format at some point. So IMZML is just an extension of the MZML format. And so IMZML is compatible with MZML. The difference is just that it adds additional terms for mass spectrometry imaging specifically, which is why a lot of the terms in here are for mass spectrometry generally. You can see some of these are coming from a mass spectrometry ontology. Some of these are coming from an imaging mass spectrometry ontology. So the start of this IMZML file just describes some of the basic things about the data set itself describes what kind of spectra are in it, MS1 for this one, profile versus centroided, so that is also stored here. It includes a universally unique identifier. This is something that is intended to link the IMZML file with the IBD file. So at the start of the IBD file, there is supposed to be another universally unique identifier that matches the one in the IMZML file. So that can be used to make sure that you're using the IMZML file and the IBD file that go along with each other. In practice, I'm not sure how many people actually check that, but that is the intended purpose. Beyond that, we have information such as the kind of instrument that this was collected from, contact information for the lab and person who ran the experiment. So this data, for example, the contact is Andreas Romp, who is one of the main authors of the IMZML format itself. So this was an example data set from one of the original publications describing the IMZML data format. Beyond that, the rest of, oh, here we have a little bit more instrument configuration. So this comes from a thermal LTQ orbit trap using electrospray ionization. Has some more information about the instrument. And then the most of this file consists of information about where to find specific spectra within the IBD binary file. So the rest of this is just describing where within the binary file we can actually find different mass spectra, as well as their positions, their X and Y positions on in the data set. So that is the IMZML part of the file, which we won't go into much further than that, but I just wanted to show you what this kind of file looks like in case you ever need to find anything in it. There do exist some IMZML checkers, or validators. So part of what Andreas Fromp's lab has done is also develop validators for the IMZML format. This comes, I believe, from Alan Race, one of Andreas Fromp's, I think, postdocs or another scientist in Andreas Fromp's lab at the time. So originally there was a Java version of this IMZML validator, which is still available if you want to download something that you can use on your computer directly. There is also a web version of this that is in WebAssembly, so it's actually relatively fast. And all you need to do is drop in let's see, where is the, yeah, so you can just drop in a local data file onto this, and the website will automatically check the IMZML file for you. In fact, I can try that real quick just to show you as an example. So here's my IMZML file. I can validate it here. This all actually happens locally, so this doesn't need to go up to any server. The WebAssembly for doing this is embedded in the website. So the file doesn't even actually get sent anywhere. So we have a couple of small issues with this file. It's actually pretty normal for IMZML files to have some minor problems because writing XML files correctly can sometimes be a little bit difficult because there's often a lot of rules to follow. So it's not super unusual that even a kind of example IMZML file like this might have a few small issues. Yeah, so it just looks like it's missing a couple tags. But nothing super problematic there. But sometimes if you're having trouble reading an IMZML file, either in Cardinal or in other software as well, sometimes the problem is just that the IMZML file itself was not written correctly. There's a lot of mistakes that can be made in writing that file. And so one thing that you can do to check that is to use IMZML validator, either this version or the Java version if you want to use that, to see what if there are any actual issues with the file itself. because a lot of times it's a problem with the file itself and how it was written rather than the software tool trying to import it. So that's one thing to one resource for you that is available. So this is just imzml dot github.io. Any questions so far on imzml? So right now, just talking about the XML part of the file. All right. And then we have the binary part of the file. So this one I can't show you because it's not human readable. It's just a bunch of bits in a file. And so the binary file is has a .ibd file name extension, and this is what contains all of the actual mass to charge ratio, MZ arrays, and all of the intensity arrays from the data collected. This can also include other data arrays that might have been collected. So if uh, you, a lot of you might not be using ion mobility yet, but if there were mobility values for the data, these would also end up in the binary file as an additional array as well. Um, don't know what we can't do anything with those mobility values really yet in Cardinal, but you can potentially access them through there. So one thing to be aware of when working with imzml files is that the format itself comes in two variants. We have a continuous variant and what's called a processed variant. And one thing I want to emphasize here is that these names are potentially a little bit misleading. The processed format does not necessarily imply that the spectra themselves have been significantly processed, or that the data is centroided or anything like that. The process part here, I suppose the original idea for that name probably comes from processing that happened on the instrument itself before it got to the raw data file. So the difference between these two formats are that in the continuous IMZML format, all of the mass spectra in it share these same mass to charge values. So they share the same MZ array. And so we only need to write the MZ array once. So there's only one MZ array in the continuous format, and then the rest are the intensity arrays. So that makes the continuous format significantly simpler and potentially easier to work with because all of the mass spectra have the same MZ values. The processed version of IMZML allows for each mass spectrum to have their own MZ values. So in the processed IMZML format, we store a separate MZ array and intensity array for every single mass spectrum in the data set. So continuous format means all of the mass spectra have the same MZ values. Processed format, all that means is each mass spectrum can have their own MZ values, their own mass to charge ratios that are not aligned or shared between the different mass spectra. Um, all right, so that's going to impact kind of a little bit of how we tend to work with these two formats and what kind of data structure you will get back in Cardinal when you first import these. But I want to make sure that it's clear that we have these two different variants of IMZML, continuous and processed, and that is also separate from whether the spectra themselves are in profile representation, so we have the whole spectrum, or a centroided representation where we only have centroided peaks. All right. Any questions on that before we move into kind of importing an example file in Cardinal? Yeah.
Does that profile, for example, like the continuous or the process, or they don't have a relationship?
Good question. So the question is, does one of these two formats correspond to profile or centroided, or can they both have both? And the answer is they can both have both. So there is no correlation or nothing tying profile versus centroided spectra to the continuous versus processed format. Yeah, sometimes it might be a little bit more common to have one in one format than the other, but they can both store either profile or centroided data. Let me close that. So I'm going to be using R Studio here for walking through this. So what I have open here is just the Cardinal 3 user guide. This is available with Cardinal every time you download and install Cardinal. It's also available from the Bioconductor website, and if I've included in the course materials for today. So I'm working on the R Markdown version of this, .rmd. You should also have available, so this is going to be in the tutorials folder in the course materials. Uh, you also have an HTML version of this that you can take a look at. So it starts off describing some of the recent update, installation if you have not already installed Cardinal. But all of this is written in R Markdown format. So this is the HTML version of this. And then I'm going to be working from the R Markdown version of this. Are you all familiar with R Markdown? Have you used this before? Uh, all right, sounds like you have, but just as a reminder, so R Markdown is just a format for interleaving um, uh, a markup language called Markdown along with our code snippets. So we can have our code chunks along with Markdown markup. And Markdown is just this markup language that allows us to do things like format headers, italicize, emphasize, create tables, all of those standard kind of formatting things you might expect from a text document. So this allows us to combine Markdown markup along with our code chunks and produce output that looks like this. So vignettes from R packages are often written in R Markdown format. And so this is what I'll be using here. So I'm going to scroll down here to our first one of our first code chunks, which is actually just on installation. I think you all already have used Cardinal at least a little bit or have it installed, but if someone hasn't yet and is watching this later, first things first you would want to do is install BIOC Manager. So BIOC Manager is the package for managing bioconductor packages. Cardinal is hosted as part of the Bioconductor project, which is a project for hosting bioinformatics related R packages. So Cardinal is part of a much larger software project on Bioconductor that emphasizes all kinds of bioinformatics, including genomics, proteomics, and mass spectrometry along with genomics and other omics Cs. So after installing BIOC Manager, you can install Cardinal from Bioconductor using BIOC Manager : install, and then the string Cardinal. I'm not going to do that. I already have it installed, and I'm going to assume that you do as well at this point. So once you have R loaded, and once you have Cardinal installed, you can load and attach Cardinal to your search path by using the library function. So library will just both load Cardinal as well as attach it to your search path, which just means that you can use functions from Cardinal without using this what I'm doing up here with BIOC Manager. So if you're curious what that is, this is just using the name of the package, a function from that package so that we can use a function from that package without first calling library on it. So that's what's happening up there. All right, so at this point, I've loaded Cardinal. You are going to see some messages when you first load Cardinal, as it is loading some other required packages. One of those includes prot generics. This is a package that includes generic functions for proteomics more generally. BIOC generics, this includes a bunch of generic functions for bioconductor generally. And then at the end, we have Cardinal itself that has been loaded. And I am on version 3.6, which is a new major update that just came out last week. So if you aren't on this version yet, this is the version that I will be using here. It is a major update that has some breaking changes. So if you have some super important mission critical workflows back at your own lab, I do recommend testing this on a separate machine to figure out any differences before deploying it on a mission critical system. But we think those changes are really worth it. There are some nice improvements that I'll be going over as we work through some of the example vignettes that we're going to be looking at today. Right. Any questions so far? All right. Okay, so I'm going to go ahead and start off by just loading or reading in an example IMZML file. So I'm going to get the local file path to an example IMZML file from Cardinal IO. So again, you can see I'm using this naming scheme just so I can use a function from Cardinal IO without first loading Cardinal IO with library first. That's all that is happening when you see the name of a package and then these two colons after that. Um, so here I'm going to take that file path from Cardinal IO, assign it to path continuous. So this is the file path to a small example IMZML file on my local machine. When you install Cardinal, you should get Cardinal IO as well because it is a dependency of Cardinal. So Cardinal IO will have been installed automatically. So you will also have this example file on your machine if you've installed Cardinal. It will be located somewhere different for you, obviously. All right, so here we have a path to a continuous format IMZML. In Cardinal, we can just use the read MSI data function to import that. So I can just give it the full file path along with the file extension, and read MSI data will figure out from the extension that this is an IMZML file and import it appropriately. So I can just use read MSI data on that. You can see that it prints out some progress messages as it's importing it, but this is a small file, so it's really quick. Tells us the file that it's importing, tells us in a couple messages about what kind of IMZML file it found here. So it tells you that this is indeed a continuous IMZML file. That's not always going to be obvious from the name of the files. You would have to check the IMZML to see what kind of format it is. So read MSI data will tell you that when we first import it. It is also telling us that this is profile spectra in this file. So it tells you both of those things right away when you import that this is a continuous file and we are importing profile spectra. So the default when importing a continuous IMZML file is to return it as an MS imaging experiment, which is a class of object we'll be spending a lot of time talking about today. If I just type the name of the file or the name of the object that got created and returned from read MSI data, I'm calling it MSC Tiny here because it's a small example file with just 9 spectra in it. You can see that this prints out some information about the data that we just imported. So it has 8,399 mass features. These are the different MZ values. And we have 9 spectra here. It tells us some more information, such as the mass range, some of the experimental metadata that got imported as well, whether it is centroided or not. We already know that this is profile spectra, so it is not centroided, and so on. Any questions so far? Are there any issues? Everything okay? All right. All right, so that was importing a continuous IMZML file, which will typically get imported as an MS imaging experiment object, which we'll talk again about in a minute. But let me also go ahead and import a processed IMZML file here. Again, I want to emphasize that the format being called processed does not actually imply that the spectra themselves have been processed beyond the basic zero data removal that the instrument did. So I'm going to use read MSI data on this again. and I'm calling this one MSA tiny because the default data structure that is returned when we import a processed IMZML file is going to be a new data structure called MS imaging arrays. So this one is a new data structure with the new release of Cardinal. So we're also going to be talking about this new data structure a bit today, which is the new default for when importing the processed IMZML format. And we'll talk a little bit about why that is and why we have a new format here. Um, okay, so let me talk to you a little bit about the different data structures that we have in Cardinal now. So these are the previous data structures we had in previous versions of Cardinal, which I'm not going to go over right now. But the short version that I want to mention here is just that we had more classes, we had more kinds of data structures than we really needed, and that had the potential to cause some unnecessary confusion and made it a little bit more difficult to sometimes work with the data than we really wanted it to be and than it really needed to be. So one of the major changes in the new version of Cardinal 3.6 is that we've done a lot of work to dramatically simplify the what we call this class hierarchy, which is the different data structures we have and how they relate to each other. So at kind of the one of the simpler levels here, we have a data structure that we call spectra arrays. Spectra arrays, if I jump back over here to our studio, um, I can look at the spectra data slot, which contains the spectra arrays for anything that I've imported from IMZML. So MS imaging arrays and MS imaging experiment will both contain a spectra data slot that contains the spectra arrays. I can see that we have this spectra arrays class here. And so the purpose of that data structure is just to store arrays of data. This is going to be storing the spectra themselves. That could be multi-dimensional arrays, so that could be matrices of processed spectra, or this could be one-dimensional arrays in the case of raw spectra. So all this class does is it stores the actual arrays of data. And if I look over here, for our MSA tiny. This is the one we imported from the processed IMZML. So this is our MS imaging arrays object. Within our spectra arrays here, we have two arrays. We have a list of MZ values and a list of intensity values. So in our spectra arrays here, we have the MZ arrays and the intensity arrays stored separately. Conversely, if I were looking at an MS imaging experiment, so I can use the same spectra data accessor on an MS imaging experiment because an MS imaging experiment is similar to the continuous IMZML format in that all of the spectra have the same MZ values. We see just a single intensity matrix here, storing the intensities because we don't need to store the MZ values for every spectrum. So that is spectra arrays. Now the spectra arrays are what is the class that actually holds this spectral data. Then we have a spectral imaging data class. This is a general data structure for storing spectra that can be used for imaging. So Cardinal is itself designed for mass spectrometry imaging, but this is a little bit more of a generic class for any kind of spectral data that has positions that can be used for imaging. And then we further specialize this class into spectral imaging arrays and spectral imaging experiment, which is where we get MS imaging arrays and MS imaging experiment, which are the two classes that you will be primarily interacting with when working with mass spec imaging data in Cardinal. So the difference between these two classes is that MS imaging arrays is designed more for raw, unprocessed mass spectra, stored as lists of arrays. So MS imaging arrays assumes that every mass spectrum has its own MZ values, and it makes it easy to work with data when the different spectra have different MZ values, versus MS imaging experiment, which is designed to work with data when all of the mass spectra share these same MZ values. Ultimately, in the course of processing profile data into centroided data, we are usually going to end up with an MS imaging experiment object because we want to process the data to a point where all of the spectra or all of our data points have the same mass features, at some point usually reduced to a list of peaks. So MS imaging experiment is designed for easier image slicing. This is the one that we can pass to statistical methods and machine learning methods, as we will later today. Whereas MS imaging arrays will encounter more during the pre-processing of data. Any questions so far on that distinction here? All right, so let me talk a little bit more now about what are the different components of these objects. So I'll go back to MS imaging arrays. So I'm starting with MS imaging arrays here because MS imaging arrays essentially contains a subset of these same slots. So the same components of the data that MS imaging experiment has. So all of the same methods that we can use to access different parts of the data on an MS imaging arrays object, we can use the same thing on MS imaging experiment, but the reverse is not always going to be the case. All right, so MS imaging arrays, these are for spectra with differing MZ values, which is also why for this kind of object, you actually don't see the mass range here, because the mass range is going to be slightly different for every spectrum. And to figure out the mass range for the whole experiment, we'd have to look through every single mass spectrum here to do that. MS imaging arrays, we treat it in a list-like manner. So we can think conceptually of MS imaging arrays as just a list of spectra that comes along with a lot of metadata as well. And so if we want to subset an MS imaging arrays object in R, we can do that just like we would a list or a vector. We can pass in a single subscript or a single vector of indices with what we want to subset the object into. So for example, here, if I'm subsetting MSA tiny to get the first 3 mass spectra, I can just use 1 through 3 to subset that data set. So you can see now I have just 3 spectra. And I am assuming that everyone has some basic familiarity with R. So if you don't, 1:3, this is just making a sequence of 1, 2, 3. I'm using those indices with the square bracket operator to subset MSA tiny. And you could use the same thing to create sequences and then subset vectors as well, any kinds of vectors. So MSA we can treat as a vector or a list if we want to subset it. So if I wanted to get, say, just the first and the 9th spectrum, I could do that as well. So conceptually, we can think of it as a list of mass spectra. If I want to access the actual spectral data, I can use the spectra data accessor. That gives me the spectra arrays slot. So these data structures that get returned from read MSI data, these have what we call slots. The slots are just the different data components that compose the data structure. So spectra data returns these spectra arrays, which contain the actual spectral data. And if we want to access either of these data arrays directly, calling them data arrays, they're actually lists of data arrays. We can use the spectra accessor. So the spectra accessor is used to access a specific component of spectra arrays. And we can do that by name. So if I want to access the MZ component or the intensity component, I can just use the spectra accessor and give that name. So there's my list of MZ arrays, for example. Here's my list of intensity arrays. But there are also shortcuts for that. So if I just use the MZ accessor, that will give me directly the list of MZ arrays. And if I just used intensity, that will give me directly the list of intensity arrays. So one thing I want to address here now that we're looking at these MZ and intensity arrays is you'll notice the way that these are printing out. These are what we call matter. These are matter list objects. So these are coming from a package called matter. Matter is another one of the packages that is part of the kind of extended Cardinal family. So matter is a lower level kind of backend package to Cardinal. It is where I have moved a lot of the functionality for working with larger than memory data, some of the low-level signal processing tools, and it also contains our new plotting library for the most recent version of Cardinal. So you'll sometimes see me using some functions from Matter at certain points. And so Matter is just an additional package that Cardinal is kind of built on top of. It provides a lot of the low-level functionality, including some of the data structures for representing the actual data, the actual spectra. So part of what Matter implements and part of what Matter provides is the ability to work with out-of-memory data without fully loading it into computer memory. So our computers have long-term storage on either hard drives or solid-state drives that can store a ton of data. But when we actually want to work with data and analyze it, we have to load that data into working memory, which we have a lot less of. And so sometimes we can have, especially with mass spec imaging, data sets that are much larger than the amount of memory we have available. So for example, on my laptop, I think I have about 32 gigabytes of memory, which is still quite a large amount relative to what people might have had on a laptop until recently. But it's still not a whole lot compared to some of the data sets that we might work with, which can get into 50, hundreds of gigabytes or even larger than that. So part of what the Matter package provides as a backend to Cardinal is allowing us to work with large data sets without loading them directly into memory, which is the default in Cardinal. So when you load a data set using read MSI data, one of the arguments to this function. And actually, one quick thing I'll note here. So if you need help for any function in R, any function in Cardinal, there are two ways you can quickly access that help. Either just use the question mark and then the name of the function that you need help with. Or if you can't remember that a question mark is for a help or question, you can also use the help function that will also bring up documentation. You can even look at just the documentation for the package in general itself. If you want to look up the index of all of the available help pages for a particular package, you can use the library function, but with the help parameter or with the help argument and then the name of the package. This will bring up the index. So this lists all of the different documentation pages that are available with that package. So any of the names on the left of the index here are the names of help pages that you can load up documentation for if you need help on how to use a certain function or how to perform a particular action. So what I was loading here was the help page for read MSI data. This currently works for IMZML as well as analyze data sets. You can see ultimately read MSI data calls either read IMZML or read analyze, which are for those formats respectively. One of the arguments to these that gets passed along from read MSI data is the memory argument. And this is an argument that you can set to indicate whether you want the data loaded into memory or not. This is a new argument in the current version. Previously, we had a similar argument called attach.only. Memory is just the new option for that. If you use attach.only, it should still work in the current version, but you'll just get a deprecation warning. So if you want to load a data set and load the data fully into memory, you can just set memory equals true. For smaller data sets, this might be helpful to load it into memory directly. For a large data set, you wouldn't want to do this. And so if I look at the spectra data for this now, so one difference you can see is these are now regular lists in R rather than matter lists. If I get, say, the MZ arrays here, you can see now this is printing out the entire MZ arrays for all of the mass spectra, which are a lot of MZ values. So these are all loaded into memory. This is a pretty small data set, even though it looks like a lot. So we have 8,000 MZ values here, but it's a pretty small data set. So I'm going to go ahead and load that again without memory equals true. All right. So by default, the actual data is loaded as a matter object. So in this case, a matter list of those arrays, which means that this data is not loaded into memory. So it's not taking up any space in memory except a very small amount. You can see, well, this is a pretty small data set, so it's not actually worth it in this case. But if this were a larger data set, you can see how much real versus virtual memory is being used. So real here, this is the amount of actual memory in use by the metadata. And virtual, this is how much data is actually being represented in the file. And we can work with these lists and arrays just like we would with an ordinary R list or array. So I can index it if I want to bring a specific array into memory, and so on. But for the most part, they work just like ordinary R lists and matrices. Any questions so far? All right, so that's the actual spectra data for MSA, for mass spec, for MS imaging arrays objects. These are going to be lists of the different spectral components. So this includes MZ arrays and intensity arrays. For an MS imaging experiment, so again, MS imaging experiment, for this data structure, all of the spectra share the same MZ values. So that means for the spectra data here, instead of lists of MZ arrays and intensity arrays, we can have just a single intensity matrix. So this by default is stored as a matter matrix, which again means it's stored out of memory. So for MS imaging experiments objects, I can just use the spectra accessor to load that matrix of intensities directly. The intensity accessor would also work here. So you can see that is a matrix for MS imaging experiments where each row corresponds to a different MZ value. Each column corresponds to a different mass spectrum at a different location. All right. So that is MS imaging arrays, MS imaging experiment, and the spectra arrays, which is what contains the actual spectral data. Now, the other part for both of these data structures are going to be experimental metadata for the actual mass spectra, for the mass features, and for the experiment itself. So there is a class called X data frame or XD frame. This is a specialized data frame in Cardinal that can contain additional key columns. And specifically, there are two versions of this that you'll be working with. One is the position data frame. The other is the mass data frame. So position data frame is just a data frame that has required columns for positions, spatial positions. So you can imagine those are giving the positions of the mass spectra. so that we can recreate the actual images, so we can plot images with that. And mass data frame is just a data frame that has a required MZ column in it. So let me jump back over here to RStudio. So for MS imaging arrays, we just have a pixel data slot. This contains the position information and any additional metadata information for spectrum level data. So any spectrum level metadata goes into this pixel data slot. I can use the pixel data accessor to access it. pdata is also a shortcut for accessing this slot. And so this returns a position data frame. It has required columns for the positions. By default, those are just named X and Y. And it also has a required column for the experimental run. So you'll see a column here for run, and that tracks the experimental run, which usually just corresponds to the slide. Not necessarily, not always, but it depends a little bit on how you've prepared the data. By default, each IMZML file that you load that was not saved with Cardinal specifically will be loaded as a separate run. So typically you would expect each IMZML file contains a single run of mass spectra from a single slide. So some additional things you can access as part of the pixel data here are the coordinates. So if you just use the coord accessor, that will access specifically the pixel coordinates for each of the mass spectra. If you want to just directly access the coordinates, you can also access the runs and the names of the runs. So run names will give the names of any of the experimental runs. By default, these are just named after the IMZML data file, the file name. And you can use the run accessor to access the different experimental runs. Let me make sure we will not be disturbed. There we go. So every spectrum has to specify which run it was a part of. Okay, so that's MS imaging arrays. So for MS imaging arrays, we basically just have the spectra data slot and the pixel data slot. We'll talk about the experiment data slot in a moment, along with MS imaging experiment. So any questions on MS imaging arrays specifically? We'll talk about processing, visualization, all of that shortly. But any quick questions on just the concept of this MS imaging arrays object before we talk a little bit more about MS imaging experiment? All right, so now let's focus a little bit on MS imaging experiment for a moment. So MS imaging experiment assumes that all of the mass spectra share the same MZ values. So that means that we can represent the data as a matrix rather than just lists of arrays. So we can conceptualize an MS imaging experiment as a matrix-like format where the rows correspond to the mass features. So we have a row for each MZ value, and the columns correspond to the spectra. So we have a column for each mass spectrum. So in this data set, we have 8,399 mass features. We have 9 spectra. So we can conceptualize this as a 8,399 by 9 matrix. And if we want to subset an MS imaging experiment object, we can do that like a matrix or a data frame. So we can use the square bracket function or method to index or subset. The first index passed here is going to be for the rows, which are the MZ values or mass features. The second index here is going to be for the columns or the mass spectra. So what I'm doing here is I would be subsetting the first 500 MZ values, the first 500 mass features, and the first 3 mass spectra. So if I run that, that subsets the data to the first 500 mass features and the first 3 spectra. One other thing I'll note here is if we are working with data that is stored out of memory, which is again the default. So this is so with MS imaging experiment, we have an out-of-memory matrix. So this is not taking up any space in actual memory. When we subset these objects, when we subset an MS imaging arrays or an MS imaging experiment, none of that data on storage is actually touched. So all of this subsetting is happening, should happen relatively quickly. You don't have to worry about that taking too long. So with MS imaging experiment, we do represent the spectra as columns in a matrix rather than separate lists. And just like MS imaging arrays, we can access the pixel data information using either the pixel data accessor or the P data accessor. So that gives us the position data frame with X, Y coordinates, the run information, and if we had any other spectrum level metadata, that could also be included in this pixel data slot. With an MS imaging experiment object, we also have access to feature data because all of the mass spectra have the same MZ value. So we can have a feature data slot that contains information about the mass features. So typically this will just include a column for the MZ values. If we have additional information about those mass features, we could have additional columns here. So feature data or F data will access that slot. If we want to access the MZ values directly, again, we have the MZ accessor function that we can use to do that. Note that MZ and intensity, these are accessors that work for both of these, but they will return different formatted values depending on whether we have an MS imaging arrays or an MS imaging experiment. So for an MS imaging arrays object, MZ will return a list of the MZ values for every spectrum. For an MS imaging experiment, it will return a single vector of MZ values for the entire experiment. And then before we get there, so one other thing I'll talk about here is the experiment data slot. So we have an experiment data slot that can be accessed with the experiment data accessor. You'll have this for both MS imaging arrays and MS imaging experiment. Looks like I spelled that wrong. So this will be an IMZ meta object. This is a class that is coming to us from the Cardinal IO package. It is essentially a very simplified version of some of the same metadata that you can find in the IMZML file. So any metadata that was stored, any experiment level metadata that was in the IMZML file, what can be stored here will end up here in this experiment data slot. So for example, here we can see we have MS1 spectra. They're stored in profile format. We have the contact name for this data set, who created it, who can we contact about it, the instrument it comes from, and so on. We have some specific imaging metadata as well, such as the direction of the scan pattern, the pixel size, and I'm guessing those are microns. Yeah, question. Um, like this? Uh, no. STR is a function for just looking at the internal structure of any object in R. So you can see this prints out the relatively complex structure of a full MS imaging experiment object. Um, so that's what this STR function is doing. The question is, does experiment data do kind of the same thing? So no. So experiment data is accessing specifically the experiment data slot, which we can actually see here as part of the overall data structure. And so this is an IMZ meta object. So this is something that is further documented in the Cardinal IO package. Let me actually jump over here to Cardinal IO. So this is the user guide for Cardinal IO. And so if you want more information about this IMZ meta class, you can check out the Cardinal IO package. It's pretty simple to use. You probably don't typically need to use it directly for the most part, unless you do want to kind of fill in some of this experimental metadata information that might not be in the IMZML file. Um, Most of the stuff here is stuff that will typically be in the IMZML file, but depending on the IMZML file and who wrote it, it may or may not be present. So you can add to this directly if you want this information to be included if you were to write the file back out to IMZML. It's pretty straightforward in that anything that you see here is just a field that can be assigned to directly, kind of like a list. So if you want to set the spectrum type, set the spectrum representation, and so on. You would just index into it like an ordinary R list, so you can use the $ accessor. Um, it's not quite an ordinary R list, so let me go ahead and assign this out to E to show you for an example. So, oops, that again. So if I wanted to assign spectrum type to something else, um, let's say I just wanted to say MS spectrum. It's not quite like an ordinary R list. It is designed to only accept valid CV param tags here. So the IMZML format is designed around a controlled vocabulary of specific terms. That was the ontology that I mentioned earlier. So all of these, for the most part, not certain things. So contact name, for example, the contact name, affiliation, and email, those can be any strings. But some of these do have to be specific terms. So for example, if I try to assign a spectrum type that doesn't actually exist, I'll get an error that tries to give a helpful message about what I might have meant. Um, so in this case, MS1 spectrum is a valid term. MS2 is not, MSN probably is, yeah. So these do correspond to controlled vocabulary parameters from in the IMZML format. And it will try to give you a helpful list of what terms you might have meant if you don't give it the exact proper term. It should also find partial matches. So yeah, so if I just try to assign MS1, it'll print out all of the possible different options that start with MS1. So you shouldn't normally need to fill this in directly, but if you do have additional experimental information that was not in the IMZML file, you could assign that into here, such as the instrument model, ionization source, things like that. And then that information, anything here will be included if you write the file back out to IMZML again. All right. So I will also mention that this IMZ meta, this is a simplified version of working with any of the IMZML tags. So again, over in Cardinal IO, we have distinct classes for IMZML and for IMZ meta. So when importing an IMZML file, there is a full parse that happens that contains pretty much almost the entire IMZML file and all of the tags in it. Again, it's more complex than you need to worry about for the most part, but there is a more complex IMZML version of this. I can actually convert this to the IMZML. There's a more complex version of this object, and this is the simplified version that is intended to be easier to work with. So you can just set some of these tags if you happen to know the metadata. Any questions so far? Okay. So now that we have a basic idea of what MS imaging arrays and what MS imaging experiment are, the other thing I want to show you is that, so right now, both of these we imported directly from an IMZML file using read MSI data. There might be times that you need to construct one of these objects kind of from scratch. So if you are working with maybe a format that can't be converted to IMZML, maybe you have data in some other format that someone else is able to write a script that you're able to import it into R in some other way. that isn't IMZML or using the read MSI data function from Cardinal. Say you just have, somehow you imported some matrices or lists of MZ arrays and or matrix of intensities, things like that. So you can construct these objects from scratch if you need to build one of these from data that you have imported in some other way. So here I'm just going to quickly simulate just a matrix of spectra. So here I've simulated using simulate spectra here, just a matrix of intensities that I can use to build an MS imaging experiment. So S intensity here, this is a large matrix. Well, not that large. A small matrix of 456 features, nine columns. Uh, so if you're constructing an MS imaging experiment from scratch, you need to construct its components. So that includes the actual matrix of intensities, which I already have that I created from simulation up here. So this matrix of intensities could come from wherever you did happen to get it from. Again, maybe someone else in your lab wrote a converter that allows you to import a matrix directly, but not an IMZML file. So I could pass that matrix of intensities to spectra data here. I need to construct a mass data frame. All that is I just provide the MZ values corresponding to the rows of that matrix and the mass data frame constructor. For that, I need to construct the position data frame. So this needs to include the run and the spatial coordinates. Excuse me. Thank you. All right, so from this is all that I need to construct the MS imaging experiment object. So I have the matrix of intensities. I have the mass data frame for feature data. I have a position data frame for pixel data, which again, those are just data frames that I can fill in with those columns. And then I can use the MS imaging experiment constructor function to create an MS imaging experiment object. So pretty relatively simple. I can just pass a matrix and data frames corresponding to the feature and pixel data. So if you do happen to import data from some other method than an analyze file or an IMZML file, so R, there's all other ways to import data into R, such as read CSV, read RDS. One way I've gotten data is in a matrix in a MATLAB file or something like that, and importing that, and then turning it into an MS imaging experiment like this. Any questions so far? All right. I think, let's see. All right. So I want to. All right, yeah, let's go ahead and talk a little bit about. We'll start talking a little bit about visualization here, and then we'll come back to this after our break as well. So, a big part of Cardinal is, of course, providing plotting and visualization methods. So the main two methods for visualization in Cardinal are either going to be plot or image. Plot will typically plot in the mass spectrum space, and image will typically plot an image of some sort. So if you see plot, that's usually going to be plotting the mass spectrum or mass spectra. So here I can use plot on an MS imaging arrays object that I'm going to actually simulate here. Do I want to do that? Yeah, I'll just simulate this for now and convert it to an MS imaging arrays. So we'll be doing this on real data soon, but just for the sake of showing the different parts of these methods and how to use them, I'm just going to use some simulated data here. So another feature of Cardinal is that it does provide functions for simulating mass spec imaging data. So there is a simulate spectra function that I used a little bit earlier. and there's also a simulate image function. Simulate spectra just simulates the spectra themselves. Simulate image will simulate the mass spectra for a complete image. There are also, there's ways to fully specify different patterns and things. So you can specify patterns of pixel data and feature data to construct different shapes with peaks in certain places and things like that. But there's also a bunch of different presets that you can use for different very basic experimental designs. So these are all documented here on the help page for this. So some of the preset images include things like just circles and squares in different corners, possibly with different conditions, possibly with across different runs, and so on. So here I just simulated some data from preset 6, which is 2 squares in the corners and a center square with 2 different conditions in different runs. So if you do have some methods to test and need some simulated data to do that, we have got you covered. All right, so I'm going to start off with the MS imaging arrays version of this. So plotting the plot function will plot mass spectra. One argument that has changed slightly from the previous version is if we want to plot a mass spectrum based on its index. So if I want to plot the 496 mass spectrum and the 1520th mass spectrum, the I argument, short for index, will indicate that that argument to plot. This used to be called, I believe pixel was the old name for that. That should, I believe, still work with a deprecated message. But I just decided to shorten that and make it the same between plot and image. So just the I argument will specify the indices of which spectra we want to plot. So here I'm going to plot the 496 and 1520th mass spectra in this little simulated data set. So you can see using RStudio, those pop up right over here. If you're familiar with with using Cardinal and plotting spectra before, you might also notice we have a new plotting engine underlying this. So we have a whole new plotting engine in the recent version, Cardinal 3.6, that was released last week. One major difference you'll see is that the faceting, the subplots here have been improved so that if they share axes, we don't print multiple axes. So these both share the same intensity axis. So we just have one axis here. And then on the x-axis here, we have the MZ values. So if I know the specific indices of mass spectra I want to plot, I can just pass those indices directly via this I argument. If I know the coordinates of the mass spectrum that I want to plot, I can pass those using the coord argument. And that can, I would typically pass those as either a list or a data frame of all of the different combinations of X and Y indices I want to plot. So let's say I want to plot the spectra at X equals 16, Y equals 16, which happens to be the ones that I already plotted here. I can do that like this. Note that in this case, this automatically seems to have resolved to just the first that it found at X and Y equals 16. So we got the first one. We can also specify the run, I believe, here. So second run. Yeah, so if we want to specify which run these are coming from. So one of the additional kind of things I didn't mention about Cardinal or Cell as part of Cardinal when I was describing it earlier is that our data structures, MS imaging arrays and MS imaging experiment, these are designed for complete experiments. So multiple data files, multiple samples, multiple runs. And so we can have multiple runs here that belong to that might have been coming from different slides and things like that. So we can plot multiple runs as well. Any quick questions on that? Because if not, it is time for our first break. So far, all we've covered so far is introduced IMZML files, talked about loading up Cardinal, introduced the MS imaging arrays and MS imaging experiment data structures. And we are just getting into visualization. We'll come back after break and continue talking about visualization and how to plot other kinds of spectra and ion images and things like that. So we'll go ahead and have a break now. It is 10:30. We come back at 11 o'clock, I believe, for our second part of this second session here. All right, so there should be some refreshments out in the hall. We'll take a half-hour break, come back and continue at 11.
I think we can also just view the name of the run, right? Instead of run equal to 1.
All right, I think we can continue. All right, so you are installed. Okay, now you need to install R 4.4 if you want to follow along. If not, that's fine, but just know that some of the things will not work as expected. One of the kind of weird things about the spring bioconductor release always seeming to sync up with May Institute, yeah, just means that our newest version comes out like the week before this course. So just to give a little additional background on that, yeah. So Bioconductor is the software project that we are a part of. It hosts all of these different R packages for bioinformatics. If you haven't already used other bioconductor packages and you are analyzing other, whether it's mass spectral data or sequencing data, I highly recommend the other bioconductor packages for those purposes as well. But it's on a twice a year release cycle. So there is a bioconductor release in the spring and in the fall. Our release is a part of that. And so, yeah, our spring release just happened last week. And so that is the reason that we're using that brand new version. And it just so happened that that was a really big update. So some things are going to be a little bit different than the previous version. So as we jump back into what we were working on, so one thing I also just want to mention as we're walking through this R Markdown document, so you do not need to run everything in here, especially the lines at the very beginning before the introduction. You don't need to run these. These are just for setting things up, setting up some options for knitting the entire document to this HTML version. But these ones you don't need to run. Just the things after that is what I would start with. And if you already have Cardinal installed, then you of course don't need to run that part either. Let's see. There's something else I was trying to say about that. And just generally because we are a small group, if you have any questions or if you're having trouble running something, or if you have any general R questions as well as we're working on this, please go ahead and let me know. Just you can just ask. Well, we're a small group. I want to make sure that no one gets left behind or anything like that. So we're happy to slow down and go at whatever pace is going to be the most helpful for everyone here. Okay, so where we were before, we had just started to talk about visualization. Actually, any questions generally about what we covered last time before we jump back into visualization? All right, so right now we are plotting mass spectra. So again, I will point out that you can bring up the help page for any function with the question mark. And some functions will have multiple options. So here you can see the plot for cardinal specifically. And so there are some additional arguments that you can pass here. So as I mentioned, I is the argument if you just know the exact index of specific mass spectra that you want to plot. If you know the coordinates and the run instead, you can pass a list of the pixel coordinates and specify the experimental run. The run will default to the first one if you do not provide that. And so here, for example, I am plotting the mass spectrum at position 1616 from the first run. I can plot this for the second run if I want. The run can be specified either just numerically as the first, second, third run, whichever, or you can pass in the actual name of the run. So I could say run B1 or run A1 for this particular data set if I want to plot either of those. So some of the standard plotting arguments are used here. So for example, if we want to change the X or Y limits of the plot, we can pass in the XLim or YLim arguments to do that. So here, for example, I can use XLim to zoom in on the section, the mass range from 1000 to 1250. And another argument that is part of the different cardinal plotting functions is superpose. So this indicates if we do have multiple spectra or multiple images later that we want to plot together, do we want them superposed on the same plot, or do we want them plotted as separate subplots? So here, if I add superpose equals true up to this earlier call to plot, you can see those two spectra are plotted superposed on top of each other rather than as separate subplots. Let me plot this one now here. So here we can see a zoomed in section at between 10,000 and 1250. You'll notice in this case, the legend is taking up a bit of space. I can actually turn that off. There we go. Helpful if you want to know which colors correspond to which pixels, but it was taking up a good deal of space right now. So you can set key equals true or false if you want to turn off or on the legend. So key equals false means that the legend will not be plotted. And so here we just see those two spectra superimposed on top of each other in that particular mass range. So that's for plotting individual spectra. So right now we were plotting an MS imaging arrays object. We could do the same thing with MS imaging experiment. But if we want to plot images, those do need to come from an MS imaging experiment object. So here I'm going to use this simulated MS imaging experiment object to plot some images. So just like with plot, with image, we can either specify the index of a particular mass feature that we want to plot. If we do that, we can use I to indicate the index. So here, for example, we have the images for the feature, the 2769th mass feature. Since we have two runs, we see both of those plotted together here. So run A1 and run B1. Just like with plot, if we want to specify only a specific run, we can do that by passing in the run argument. So here I can just plot the first one. I could plot the second run, or I can specify those by name as well. And you can see this is a part of our new plotting engine that we just have a single color key for the different subplots that all share the same color key. So we can either plot based on index, so that was the 2769th mass feature, or we can actually pass in the MZ values. So here I can plot for the MZ at 1200, which is what I was plotting already. So one thing you'll notice here is that if I don't have to specify the exact mass to charge ratio, because that would be quite difficult. I just have to specify it accurately enough that Cardinal is able to figure out which one that I'm talking about. So 1200, the closest ion image or the closest mass feature MZ value to that is 1200.1599. So that is what is getting plotted. If I switch to 1201, again, get a different, let me see, so I can trying to find an example of one that isn't actually in the data set. Let's see. So this goes from, so let's try 396 actually. So one thing that you'll notice, I tried to include some helpful error messages so that you know what MZ value to specify if you specify an MZ value that couldn't be easily matched to one of the mass features in the data set. So depending on the resolution and how much distances there are between different MZ, you can sometimes get this for MZ values that are within the mass range. Here I had to choose one that was outside of the mass range to get this error. So here you can see that if Cardinal could not figure out which feature you intended, it will tell you the MZ value of the nearest MZ value of the nearest mass feature. So here it's telling me the nearest is at 396.63. So I can probably just do 0.6 and that'll get me close enough that it's able to figure out which one I meant.
What's the default threshold?
So the question is, what is the default threshold for that kind of matching? It actually depends on the MZ values of the data set. So it's based on what is the smallest gap between MZ values. So it just depends on how far apart the actual MZ values in the data set are. All right, so that's plotting a single mass feature. So if you just give it a single MZ value with no other arguments, it'll just plot that single MZ feature, which may or may not be binned in the MS imaging experiment. We'll talk a little bit more about that, but in this case, this is just simulated data. So it's just plotting that exact mass feature. If you want to kind of summarize over a small mass window, when plotting the image, you can do that as well. So the new argument for that is tolerance to make it consistent with the rest of the functions and methods in Cardinal. The old version of this argument was called plus minus. Here I've updated it to be named tolerance just for consistency with everything else in Cardinal. So you specify the tolerance, and that specifies basically the half bin width for the mass window to plot the image from. You can specify the units for that tolerance, so that can be specified either in exact MZ units or as parts per million. So you could also specify this as ppm if you want to specify it that way. So here I can plot the image for ranging, that is basically the plotting the image for the mass window from 1200 plus or minus 0.5 MZ. I could do this, as I said, with ppm as well. So here I'm plotting it for 50 ppm, which isn't actually wide enough for the simulated data. It's a simulated data, so there's actually quite a width between the MZ values here. So there it is, plus or minus 500 ppm, for example. I mentioned we can specify a specific run. We can also specify a general subset. So if we only want to plot a subset of an image, we can do that as well with these subset arguments. So here, for example, I'm saying I only want to plot the portion of the image that comes from either the circle in either of the two runs. So this just happens to be columns that are already in pixel data. So if you use simulate image to simulate an imaging experiment, part of the metadata columns are going to be whether a pixel is part of a shape in that simulated data. So that's where these columns are coming from. So there is an example of just plotting a subset of the pixels in the image. So part of image plotting is that a lot of times the images need some additional processing to look better or to allow us to more easily interpret the images and see the patterns in them. So Cardinal provides a few image processing methods that are part of this image method. So for example, you can smooth the image. So we have different image smoothing techniques. So Gaussian smoothing is one of them. We can do adaptive filtering. So Gaussian is just a simple Gaussian blur. Uh, Adaptive is using a version of bilateral smoothing, which tries to preserve edges better than Gaussian smoothing. So either adaptive or bilateral options are going to uh, preserve the edges a bit better than the Gaussian smoothing option. Sometimes they can also preserve more noise than you might prefer. So that's one of the potential drawbacks to using those. So bilateral filtering, you can see, works pretty well in this case. Adaptive is maybe adapting a little bit too much to some of the local noise there. We have a few other options for image smoothing. Diff is stands for anisotropic diffusion. So this is using a diffusion filter. Um, and then the last option, or one of the last options here, is the guided filter. So a guided filter is similar to the bilateral filter in that it tries to preserve edges a little bit better, but using a slightly different technique. So kind of the main ones to remember for smoothing would be Gaussian, which is just a very basic Gaussian blur. Sometimes that can lose edges. Bilateral and guided are some of the preferred edge preserving ones. So that's smoothing. We have multiple options, and I believe it's you have something that isn't. If you have something that doesn't match, you can see all the different possible options here. Some of these are just aliases for the same thing. So like adapt and adaptive will both be the same adaptive filtering method. All right, so that's smoothing. And then a lot of times contrast enhancement is also necessary. So uh, contrast enhancement is used when there might be certain hotspots. So one challenge with interpreting ion images with mass spec imaging data is sometimes that there is a lot of noise that can make it hard to interpret the images. In this case, with the simulated data, not so much. But in a lot of cases, we might need some contrast enhancement. So we have histogram-based contrast enhancement, which basically tries to take all the intensities in the image and kind of flatten them out, spread them more evenly across an imaginary histogram. And we also have a method called contrast limited adaptive histogram equalization, which is a variant of histogram equalization that tries to adapt to the different regions of the image a little bit better. So if you have a more heterogeneous image, the adaptive uh, histogram equalization might do better. So both Clay-He and adaptive are aliases for the same kind of adaptive contrast enhancement there. Any questions so far? Is everything running okay? Everything, any problems I can help with? All right. So those are some of the options we have here for plotting images. Smoothing, contrast enhancement, we'll see plenty of examples later today where those are useful and necessary. And then one of the last options here as part of plotting ion images is scaling. So if we are plotting multiple images, actually, let me go back up here. Plot this one. So again, with the simulated data, it's not a big problem, but when we're plotting multiple ion images, sometimes one of the images will have a much different intensity range than the other image. And so it can be hard to compare them. Sometimes you want to keep that so you know that, okay, this feature is just a lot more abundant than this other feature. But sometimes you want to compare the patterns rather than the actual intensities. And so there is a option called scale, and that decides whether all of the images are going to be scaled to the same intensity range or not. Um, There's an older version of this argument called normalize.image. There's only one option for it called linear. So I just turned it into a true or false called scale option. So with this case, not super obvious what the difference is because the simulated data is pretty clean. Might see a difference a little bit more there. Not really. So the scale option will scale all the images to the same intensity range so that they are more easily comparable so that you can look for patterns between them without one of them being kind of hard to see because of a different intensity range. And you'll see when you turn scale on, you'll see the little percent sign there, so you know that this is just relative out of 100% of whatever the intensity range is for a particular image. If that is false, which is the default, then each image will have its own intensity range, which is just whatever the intensities are for that. Um, then this last example here, you can see, so just like I can pass in multiple locations if I want to plot multiple spectra, I can pass in multiple MZ values if I want to plot multiple images. So here I'm plotting both 473 and 1618. I can turn superpose on. So if I set superpose equals true, those images will be superimposed on top of each other. Otherwise, they would be plotted separately as separate subplots. Any questions so far on plotting images? All right. And then one thing that you might often want to do, and we won't go too much into this, just a quick example, is select a region of interest in an image so that you can use that for labeling, annotation, things like that. So there is a select ROI function for selecting a region of interest. And oops. Not sure what is going on with that. That. Oh yeah, I did not update the names of the runs there. All right, so let me just do this. There we go. All right, so for example, here I'm selecting a region in the first run using this MZ value as a kind of reference. So here, for example, I might select this circle. I can click finish to finish that. Uh, there shouldn't have been multiple runs selected. I might need to update how that works. Right. Do that again real quick. Finish. That's strange. Well, that's something for me to check out. I only have one run selected, so I'm not sure why it's telling me that I'm getting multiple runs. So that's something that I will go ahead and double check in the release version and fix that if there is an actual issue there. Either way, I do know that I think I need to update select ROI so it is aware that the run argument on its own exists. So I'm not sure what's going on with that warning message, but certainly this will work fine if you only have a single run in your experiment, and I will make sure and check this and make sure it is working if you have multiple runs. But that is how you can select a region of interest. What that returns is a logical vector as long as the length of your data set. So you have a true or false for every single pixel in the data set, for every mass spectrum in the data set. And you could potentially assign that as a column. Let's see. As a column in the pixel data. So you can see I have a new column there indicating whether whether a mass spectrum belongs to that region of interest. And there is also a convenience function in Cardinal called make factor that you can just pass some logical vectors to with names, and that will turn those into a factor. So if you want to create a categorical variable with different regions of interest, you can use the make factor function for that. Yeah. So if you want to get the XY coordinate for, if you only want the XY coordinates and not even necessarily the indices of the pixel in the data set, then you don't even need any Cardinal tools. There is a function called locator that Cardinal uses internally to do all of this. So you could just do locator and then click on a pixel, and it'll return the coordinates of that, of wherever you clicked. This returns the exact coordinates, so the XY coordinates will be slightly off from the coordinates in the data set. But if you just want the coordinates, locator will do that. The first argument to locator is just the number of pixels that you're selecting. So if I chose 2 there, it would let me choose 2 locations before printing out the X and Y coordinates for all of them. And if you want the XY coordinates of a particular region, all you would need to do is subset the coordinate data frame. So for example, like this, I can see what are the X and Y coordinates of all of the pixels that were contained in that region that I selected. And then if I did want to, again, select just specific pixels rather than a region, I can change the mode here to pixels. And then rather than figuring out the region that is contained within the kind of outline that I select, it will just return the indices of the specific pixels, or at least the closest pixels to what I'm selecting there. So region is what I did before. It'll give me the region that is enclosed by my selection. Pixels if I just want to select individual mass spectra. Yeah.
Because now I change in the code like run A1 and run A2. And
yeah, so I did have it wrong before. So so to work, this should either be equals run MSC in or equals run A1 or run B1. A simpler version would also just be run equals 1 or 1 or 2. So select ROI in general takes the same arguments as the image function. So anything that you pass to select ROI actually just gets passed along to the image function. Are you able to figure it out? That's weird. Was it, is it, a single run? That's so I don't want to spend too much time on this because we have plenty more to do. And so I will go ahead and move on. But I will note that probably part of the reason that this sometimes has issues working is part of it might be an operating system issue, and part of it is sometimes an RStudio issue. So one thing we were having some trouble just now and on Windows. So the fact that it's on Windows might be part of it, which is not. I don't necessarily think that's a Windows problem in general, but the RStudio implementation of the RStudio graphics device might be slightly different on Windows, which might be have something to do with this. Um,
Because I tried locator and it was showing wrong coordinates.
mm.
And Andreas also had similar issue.
Okay. So yeah, so part of it seems to be a Windows issue. Part of it is also an RStudio issue because RStudio adds this RStudio has its own graphical device. So just a quick kind of primer, since this will be helpful generally on how graphical devices work in R. In R, R's plotting mechanisms work on this idea of having different graphical devices that we can plot things to. So you can see what graphical devices are available using dev.list. If you're using RStudio, you'll see an RStudio graphical device. And the way that RStudio makes this work is it basically creates an image of your plot and then plots it here. So RStudio is going through a couple additional layers with its plotting mechanism. So sometimes it can be a little bit buggy with how that works. Um, since I work primarily on Mac, that's usually my main testing system. So sometimes I don't catch some of the ways that RStudio behaves on Windows, for better or worse. RStudio itself has some issues with the locator function generally, in that I had to jump through a few hoops to get this plot to actually update on each call rather than it not updating properly in the first place. So um, so one thing that you can do, if you're having issues with RStudio specifically, is always you can always open a new graphical device outside of RStudio as an additional potential troubleshooting step if you're having trouble with the RStudio graphics device. So let me try this out here real quick, just to show you. So here I am now have a separate graphical device window open over here. Um, So here, hit escape rather than the finish button. So here I clicked escape, and the logical vector got returned to me as well for my selected region of interest. So if for whatever reason you're having trouble and it seems to be the RStudio graphics device itself, you can open a new one outside of RStudio that will hopefully avoid those issues. Turn that off so that we just, okay. But in any case, the part of this issue that is me, which is this warning message, I will fix and put out a new patch with the fixed version of this. I'll figure out what's going on with that. The RStudio issue I can't fix directly, but I can for sure tell you how to kind of work around it. And that is something that we're hoping to improve on in the future with like a browser-based selection for this kind of thing in the future.
How do you outside of RStudio?
So you can try dev.new. That should work. Yeah, so dev.new. If that doesn't work for you for some reason, it will depend a little bit on your specific operating system. So I believe on Windows, the graphical device is just called Windows. So if you're on Windows, you should be able to just just call a Windows function. I can't do that on Mac because I have a different graphical device. So on Mac, the default is Quartz. But if dev.new doesn't open one outside of RStudio, you can try the Windows function to do that. So right now, so dev.list will usually not list anything until you've actually made at least one plot. If there's no devices open at all. So like this, for example. So right now there's no graphics devices open. So dev.list will return null if there's nothing open. Once I plot something, then you should at least see RStudio graphical device and potentially one other thing as well. All right, so we'll see some more plotting options in a bit as we work on when we move on to working with some real data. But one last thing I want to point out here is saving plots. So if you are in RStudio, you do always have the option of just going over and clicking the export button to save as an image or save as a PDF, whatever is in the viewer here. A much more reproducible way to do this if you're creating a bunch of graphics and want to make sure you're getting the same graphics each time you run it, or if you just have more than you want to do manually like this, is to take advantage of R's graphical devices like this. So like I said, R has this idea of different graphical devices to which it plots, and the way that exporting plots to either image files or PDF files is also using this exact same idea of creating graphical devices. So this is actually very relevant to us right now. So for example, here, let me create just a file name for a temporary file. Temp file just creates a temporary file name that I can use without having to worry about this existing later on. So obviously, if you're exporting an actual image, you'll give it a useful file name. I just made this as a throwaway file name. And then if I want to export an image to, say, PDF, I can use the PDF function to create a PDF graphical device. That takes some arguments such as, firstly, the name of the PDF file to create. You have some other options such as the width and height of the plotting canvas. This is in inches, which I know might not be necessarily very intuitive on a computer, but that's how PDFs work. That's just how this works. So you can specify the width and height in inches there. And the way that all of this works, as you'll see, I now have a PDF device. dev.cur will give me the current plotting device, which is currently PDF. And so what that means is any images or any plots at all that I plot in R, just generally, whether it's from Cardinal or otherwise, will get plotted to the PDF file rather than plotted to here in RStudio. So anything that I plot right now will go to that PDF file. So you'll see no new image was plotted here. Let's create another one at, say, 1300. 1400. So you'll see this plot is not updating. These are actually being plotted to the PDF. And then when you're done with whatever images or plots you want to send to the PDF, you can turn dev.off to turn off the current plotting device. So because that was PDF for a moment there, the PDF was what was turned off. Dev.off will then return the new active device. So that's why it's returning RStudio GD here. So that just means the RStudio graphics device is now the active graphical device. So now if I plot anything new, it's going to show up here in RStudio. So let me go ahead, PDF file. Let me find this. So, oops. So obviously, if you're doing this at home, you'll give it a file name where you know where you saved it. I gave it a temporary file name that is hidden in some temporary directories. So let me find the one that I actually created here. I think it's this one. All right, so yeah, so here you can see the output of this. Seems slightly lower resolution than I would expect. I'm not sure why that is. But in any case, so here is the output PDF file. You can see that new plots just show up as new pages if you're plotting to a PDF. You can also plot to an image file, so I could change this to PNG or TIFF or different other graphics formats. So I could export to a JPEG, a PNG, or a TIFF instead if I wanted to export to one of those file formats. Those will take different arguments. So the width and height of these are generally going to be in pixels, whereas the one for PDF is going to be in inches. Any questions on any of that before we continue? All right. So that's exporting of plots. That works for any kind of plot in R. So that is kind of the preferred way to reproducibly export graphics from R generally, not just Cardinal. So any plots that you want to export in a reproducible manner, that's how we generally do it in R. Yeah. Good question. So the question is there a way to plot only the image with nothing else as part of it? So let's see. Try to, so we have a, so one thing I'll say is because we have a new plotting engine, if it's not easy to do that right now, I can make it in the next version. Trying to remember if there's an easy way to do this right now.
Way I do it is just use slides, get the matrix, and then use.
Yeah, so that's one way we can do it. I'm trying to think if there's a preset that I have available right now that would yeah, yeah. So there's not a direct way to do that using the image function directly from a data set, but that's certainly something that I can add as a style here. So I'll answer the question in a moment with a way to do that now. But to introduce a way that we can potentially do that in the future, there are some different preset styles here that we can use to modify the appearance of the plots. So the one that I'll note just here is our dark style. So the default in Cardinal is a light background with transparency. A lot of MSI software uses a dark background instead. So we just have that as an additional option if you want. So you can use that by passing in the style argument to any of the plotting functions. A way to go back and turn that off. You can set that kind of cardinal wide using the visi underscore style function. So let me change that to dark. So then any new plots would use the same style. Let me go back and turn that off for now. All right. So at some point in the future, I can add a like a minimal style or something to turn off axes and things like that if we want. But to answer that question, so I'll skip ahead a little bit to another function that we have. So if you do actually just want a slice of a sliced image with just the intensities of that slice, you can use the slice function to do that. This takes, I believe, essentially the same arguments that image does. Yeah, basically. So I can pass in MZ1200 just like before. I'll assign that to a variable I'll call X. And so what this will return is either a matrix or an array with the sliced image. So this one is an array because we have two runs. So I have a 32 by 32 by 2 array here. So the first dimensions here are going to correspond to the X and Y dimensions. The third one here to the runs. And if I do specify multiple MZ values, that will become the fourth dimension here. So let me go back and actually just choose a single MZ value and a single run. All right, so that's just a simple matrix. So at that point, I could use, for example, either the image function in base R, or what I'll actually use here is the plot image function from matter. So that will do that. But what I want here, so I want to turn off axes, trying to remember all the correct options for that. So for example, XAXT and YAXT, these are the options for turning off axes. N just means none. So if I want to turn off axes, I can use these arguments. So you can see that this is using base R's image function, which is just working on a numeric matrix. So here you can see that one thing is the aspect ratio is not set. So if I want to ensure an aspect ratio of 1, so one dimension in both directions is the same, I can set ASP equals 1. So there we have that. And actually, let me start from scratch. All right, so there's some other things I need to turn off. Turn off the bounding box. Clearly I want to change the padding. Let's see, so what's that now called? So at this point, we're just getting into some of the base R plotting parameters. And I'm trying to remember what some of these are. Margin, maybe? That helped a little bit. All right, so I won't go through figuring out how to make that look perfect, but this will at least help you get started. So at this point, I just used slice to So I use slice to get just a numeric matrix of the image. So X here, this will output a numeric matrix or an array if we have multiple runs or multiple mass features. And then I can use the image function, which here is just the base R image function, and pass in whatever additional arguments to that. One of those being colors. So if I want, I can choose, oops, let's do CPAP. Oops. It's neither numeric nor character. All right. Okay. So you can change the color scheme if you want as well. So HCL.colors is for getting various continuous color schemes. So the default for HCL colors is the Veritas palette, which is the same as our default that we've been using. And the argument here is just how many colors to use. So how many color bins in the image. All right, so again, that's just using base R's image plotting function. So if you want to further customize that, you would use any of the kind of base R image graphical parameters. So the par, looking at the documentation for the par function has how you would change things like the margins and stuff like that if you want to get it on just the image. An alternative way to do something like this would also just be to do it afterward and just say crop a PDF file. So there's another way that we could do something like that. Uh, save that. All right. All right. Any questions on any of that so far? All right, so we will come back to visualization again when we get to some real data sets. But now let's move on for now to some of the common operations that we might have on these MS imaging data sets. So one thing we've already covered is subsetting. So one of the ways that we can subset these objects is just with the square bracket method. So that's the same way that we would subset a vector, a list, or a matrix in R. So for MS imaging arrays, again, we can think of that conceptually as just a list of the spectra. So we can subset that like we would a list or a vector. So here, for example, I'm getting the first 5 mass spectra from this simulated data. For MS imaging experiment, we can conceptualize that as a matrix where the rows are the MZ values, the columns are the spectra. And so here, the first index, this is going to give me the first 10 images or the first 10 MZ values and the first 5 spectra. So we can't always just subset using those square bracket accessors. For that, of course, it helps to know the actual indices of the mass spectra or the MZ values that you want. So there are convenience functions for finding the row and column indices that correspond to certain mass features or certain positions. So we have a features method. This will return the row indices in an MS imaging experiment corresponding to certain conditions, such as the MZ value. So here, for example, if I want to find the row of this MS imaging experiment that corresponds to MZ 1200, I can use the features function here, just pass in MZ equals 1200, and that'll give me the closest, within a certain tolerance, like the closest MZ value to that. So that would be row 2769. Can also pass in conditions. So here, for example, I'm getting the row indices of all of the features from 1199 to 1201. So we have 4 4 rows that correspond to that mass range. If I want to find specific column indices that correspond to particular spectrum, I can use the pixels method to do that. So this can take in lists of coordinates, for example, or I can give in conditions again. So maybe X and Y coordinates that are less than 3 and a particular run, for example. So that gives me the pixel indices that correspond to that. So I can use these to select certain rows and columns that I can use for subsetting here. So here, for example, I'm getting all the features, mass features between 1199 and 1201. Here I'm getting the pixels, so the mass spectra IDs that are X and Y less than or equal to 3 in the first run. And I can subset the experiment like that. So there are also some kind of convenience functions for doing all of this a little bit more easily. So we have the subset function itself. So the subset function comes from base R. This works on basic data frames, for example. So here I have the basic iris example data frame from base R. So this is just a bunch of measurements on flowers. So from base R, the subset works such that I could say species equals setosa or something like that. So one of the things to remember about the subset function and the variance here are that these use what we call non-standard evaluation. So I can refer to, if I were talking about data frames, I can refer to the names of columns in that data frame as if they were variable names. So notice here, for example, for this iris data set. So here is the top of that data set. So species is the name of a column in this data frame. Species is not the name of a variable in my global environment, but because of how subset works with this non-standard evaluation, I can refer to the column names in this data frame as if they were variable names. So I can use them, I can refer to column names for comparison. So checking for where species equals setosa in this case for the flower species. So you may have noticed a moment ago that the same is actually true for both these features and pixels methods, and then for the subset methods for the MS imaging experiment and MS imaging arrays as well. So features here, you'll see I can refer to columns in the feature metadata as if they were variable names. So I can refer to the MZ column directly like this. I can refer to the X, Y, and run columns directly as if they were variable names in the pixels method as well. And then when I get down here to subset, with subset, I can also refer to columns in the either pixel data or feature data data frame slots as if they were variable names. So the first argument to subset here for MS imaging arrays, because MS imaging arrays are essentially 1D, so we just have the spectra. So the argument to subset for MS imaging arrays, the conditions here can use any of the columns in pixel data. So here I'm just referring to X and, X, I guess, X and, that should be X and Y. So here I can refer to the X and Y columns from pixel data. So I can use that, and that will subset to include only the spectra with X and Y coordinates less than or equal to 3. I can do the same thing with an MS imaging experiment, but since with MS imaging experiments, we have 2 dimensions. The first one for the rows, which are the MZ values. The second dimension is for the mass spectra, or the pixels. So subset for MS imaging experiment takes 2 arguments. The first one corresponds to the rows. So this will be evaluated in the context of the feature data. So I can refer to any columns in the feature data which will at least be MZ. And then the second argument will correspond to conditions in the pixel data. So I can use the names of any of the columns from pixel data for this second argument here. You'll notice here that I can join multiple conditions with either and or the or operators. So one thing to be aware of when it comes to the and or operators in R is here I am using what we call the vectorized versions of these. So in R, there are both vectorized and unvectorized versions of these logical operators. So the double and or the double bar, those are the non-vectorized versions of these. The single and the single bar, these are the vectorized versions of these. What that means is that if we pass in a logical vector like this, the non-vectorized version will expect, well, firstly, the non-vectorized version expects conditions that are of length 1 on either side, so just true or false on either side. And so I'm actually getting an error because of that. Depending on your local settings, you might just get a warning instead. I'm not sure. It depends on your local R settings. So that's the non-vectorized version. It expects a single value on either side. Whereas the vectorized version, so using a single ampersand or a single bar, will evaluate these element-wise. So true and true is true, false and true is false. So I can use the vectorized and if I want all of these conditions to be true, or I could use the vectorized or if I want either of these conditions to be true. Oh yeah, X and Y. All right, so here, for example, I'm subsetting where the masses are between 1199 and 1201, and where the X and Y coordinates are less than or equal to 3. So that gives me four mass features and 18 spectra there. And then lastly here, so subset expects those two arguments, both for the rows and for the columns. If you only need to subset in one direction for MS imaging experiments, we also have subset features and subset pixels. So subset features will, like it sounds like, just subset the mass features. So if you just want to subset based on the MZ values or other mass features or metadata that correspond to the mass features, you can use subset features. So here, this will just reduce me to those 4 features, but keep all the same spectra. Subset pixels will do the same thing, but for the pixels for the spectra instead of the features. So here I can use subset pixels to get me just the spectra with positions where X and Y are less than or equal to 3. Question is, can we use and here? So yeah, so one additional difference between the subset function and subset features and subset pixels is subset itself expects specifically 2 arguments for an MS imaging experiment or just 1 for an MS imaging arrays. That's because for MS imaging experiment, one of those arguments will correspond to the rows or mass features. The second one will correspond to the columns or the spectra. So if I want to combine multiple conditions here, I must use the AND operator. Whereas for subset features and subset pixels, these can take as many conditions as we want to pass, separated by commas. And all of these, any conditions passed to subset features or subset pixels will be implicitly joined by AND. So this is the same thing as doing this. Either of those will work. So this and this are equivalent, as are this and this. So we can use the AND operator, or we can just separate by commas for those cases. Any questions so far? All right. This next thing we already covered briefly, but just to revisit this, if we want a slice of a particular image, we can get that using slice. So it happens that the more convenient way of storing mass spectral data is, well, surprise, surprise, storing the actual mass spectra together rather than storing the images together. And so with the way that mass spectra are stored, MS imaging experiment, what we actually have is a matrix where the columns correspond to the mass spectra. The rows correspond to basically the flattened images across all of the runs in the data set. And so if we do want the actual images just as a numeric matrix or a numeric array, that is where this slice function comes in because it doesn't really make as much sense to store the data that way, but we might want to work with the data that way. So that's why we have a separate slice function for just returning a matrix or an array of those images. So this allows us to treat the data kind of like a data cube, where we have the two spatial dimensions and an additional feature or run dimension. One thing I'll note while we're on this topic as well is that Cardinal is set up to work with non-integer pixel coordinates. So it is possible that we have non-integer pixel coordinates here. So the values that you see for X and Y here will not necessarily, they will usually be the actual coordinates that are used for the pixels in slice. But if we do happen to have a non-rectangular image and non-integer pixel coordinates, it's possible that those will not map perfectly to a raster array. And so slice will actually do some computations to project whatever the actual pixel coordinates are onto a regular raster or raster matrix. So that's just one additional thing I want you to be aware of, is that there is a possibility that these are non-integer coordinates, and the sliced image has had some additional computations done on it in order to map those pixel positions to the actual raster grid positions. Any questions so far? All right. No problem. So as we said, with slice, the first two dimensions here will be the spatial positions. The third one, if available, will be the runs, and then the last one will be the features. By default, this will return an array. You can also turn drop equals false if you want to keep all of those dimensions, regardless of whether or not you need them. So by default, any dimensions of these that are only length one, will be dropped. You can turn drop equals false to turn that off and keep all of those dimensions explicitly. There's also a simplify argument here if you want to return the image slices as a list rather than an array. So here, for example, I turn simplify equals false. So the outer list corresponds to the different mass features. The inner list corresponds to the different runs. And then I have a matrix for each of the images within that. So that might be useful if you have multiple runs and they have very differing positions. Because sometimes you do have differing image sizes for different runs and things like that. All right, so the next thing we'll cover here quickly is combining data sets, something you might need to do frequently. So if we do have multiple data sets, so here I'm just going to subset our MS imaging experiment to a separate data set for each run. So here I did that just using the square bracket method. So here I have a variable for the first run. Here I have a variable for the second run. Each of these contains 10,024 spectra compared to the 2,048 spectra in our original data set. So if we have separate two data sets and they have the same MZ values, we can just combine them using cbind. Cbind standing for column bind. So this basically is treating this MS imaging experiment as a matrix and combining along the columns. So after doing that, we get both of those combined together with all 2048 spectra. So the thing that you do need to be aware of when combining data sets like this, or at least when combining MS imaging experiments like this, is that they do need to have the same MZ values. So if the MZ values between both of those are not identical, you will not be able to combine them. So that you might need to do some additional processing potentially in order to get the data where you can combine them. If you do have MS imaging arrays, though, so MS imaging arrays will be more common with unprocessed data, with raw profile spectra. If you do have MS imaging arrays, because these can be treated as a simple list, it is a lot easier to combine the MS imaging arrays because we do not have to combine along an MZ axis. We are just essentially combining two lists. So you can just use the C function as you can to combine lists and vectors in R anywhere. You can use that same thing with MS imaging arrays. If we want to combine MS imaging arrays together into one big data set, we can just use the C function to do that. All right. Any questions? Any other questions so far? Okay, let's see. So a few more. One other useful accessor here that I'll mention is the centroided accessor. So if you want to know if a data set has been centroided or not, you can just use centroided on that. It is possible for this to be NA for missing, because sometimes the IMZML file will not specify, or if we're importing from some other format like analyze, that information won't be available. So it is possible for that centroided to be missing. There is also an isCentroided function, which is equivalent to doing is true on the output of centroided. So that will only return true if the centroided slot is absolutely true and not missing. So that's one thing useful just to know whether the data has been centroided or not. That is also printed out as part of the object summary. And then let's see how much more we have on this. All right, summarization and then processing. All right. Okay, so one of the manipulations that we might want to do to our data set before we even get to any pre-processing is summarizing it. So calculating something like the mean spectrum or the total ion currents of all of the mass spectra. These are some things that we might want to calculate. So we have two functions, summarize features and summarize pixels, that make it easy to calculate statistical summaries over the entire data set. These both also take optional grouping options. So if we wanted to calculate the mean spectra for different groups, for different regions, or if we wanted to calculate, can't think of a good example for this one. So I can think of, if we want to calculate mean spectra for different regions, then we can do that by passing in groups. We could do the same thing with summarized pixels if we have different groups of features that we want to summarize. So the default for both of these, actually, let me pull that help page up again. So the default for these will be, for summarized features, the default is to calculate the mean spectrum. The default for summarizing pixels will be to calculate the total ion current for every pixel. You can set this stat argument to any supported statistical summary. So specifically, that includes minimum, maximum, product, sum, mean, variance, standard deviation, any, all, and the number of non-zeros. So all of those are, so these functions are set up and designed to calculate those summary statistics relatively efficiently. So even if the data is stored in a file rather than in memory, these functions will iterate over the data in the file in a intelligent way so that this calculation is done efficiently. So for example, here, let me calculate the mean spectrum. So the way that these functions work is to return an MS imaging experiment object. So you input an MS imaging experiment object, you get back an MS imaging experiment object, where the only difference is the summarized statistics have been added as new columns in either feature data or pixel data. That is a different behavior than the previous versions, but I think it will be generally more convenient for how we often work. So summarize features, summarize pixels, both of these will leave the spectra unchanged, leave everything else unchanged. The only thing that they will do is they will add a new column in either feature data or pixel data, respectively, with the summary statistics that were calculated. So you can see for summarized features, I just assigned the output to a variable of the same name as before. And we now have a column in the feature data called mean. So this is the mean spectrum that we just calculated. And if I want to plot a column in the feature data for an MS imaging experiment, I can just call plot on the object. And the second argument can just be the name of a column from feature data. So here I'm plotting the mean spectrum. Oh wait, because I was showing centroided before, I accidentally turned centroided to true, which is not the case. This should be false, which is why it's plotting a little bit strangely. It thinks these are peaks rather than a profile spectrum. There we go. That makes a little bit more sense now. So here's the mean spectrum for this simulated data. You can see we have a sizable baseline. Here I can calculate the total ion current for each of these. So here again, like before, the output is going to actually be a new column in the pixel data. So we now have a column called TIC in the pixel data. I can see that new column here from pdata. And I can use the image method, just like before, to plot a column in the pixel data. So if the second argument is a string giving the name of a column or columns in pixel data, those columns will get plotted instead of intensities. So here I'm plotting the total ion currents for all of the mass spectra here. One thing you'll notice a few places is I'm using some color palette functions. So these are functions that are exported from Cardinal from the matter package. So if you just want to choose either a continuous color palette or a discrete color palette, these are just convenience functions that return something that can be passed to the cardinal color arguments here. And you can set these palettes to different things that are available. These are both actually just using the base R HCl colors and palette colors options. So if you want to know what the options are, HCl palettes, HCl pals. So these are all of the continuous options that are available that you could set for CPAL. And then these are the different discrete options available. So these are the discrete color options that would be used for different groups or different clusters and things like that. So these are the palette colors that you could set for the DPAL, discrete palettes. All right, so here I was just calculating the TIC and plotting it. One thing you'll notice about this stat argument is if I give it a name, the name will be used as the column output. So here, the actual statistic that I'm calculating is the sum of the intensities for each mass spectrum. But I can give it a name so that the output column is called that name. So here I called it TIC for total ion current. Like I said, we can pass in grouping variables here. So suppose I want to calculate the mean spectrum for different regions. So here I have a, oh, did I not select that earlier? Maybe I'll do that condition. All right, so if I want to summarize over different conditions or different regions or something like that, I can pass in a grouping variable to this groups argument. So this can be any kind of vector that specifies a group that every pixel belongs to. So here, let me do that. So let me look at the feature data. So you can see the output of that just prefixes the region and then a dot, and then the name of the summary statistic. So here I had two conditions, A and B. And so when using those as grouping variables, I get two output columns in my featured data. One is the mean spectrum for A, the other is the mean spectrum for condition B. And then I could plot those here. Yeah.
You can also use the vector from select R.
Yeah, yep. So this actually, let me see what the different what I have here in my pixel data. So a bunch of these are just from the simulated the way that the simulation preset is. Let me use something logical here, like square one. Just make sure that works actually. Yeah. So anything that can indicate groupings, so true and false also works. I believe internally it's all just coerced to a factor internally. So here I can plot those two different mass spectra, those two different mean spectra. So if I pass a character vector as my second argument to plot, it'll plot all of those columns. So here I see the two mean spectra from those two different regions here. I can do the same thing with summarized pixels. If I have different feature groups, maybe I have different mass ranges that correspond to, say, lipids and metabolites or something like that. If I wanted to summarize something over those different groups, I could do that here. So here I have the sum, so the total ion currents for those different regions. If I wanted to do that. Oops, what are those? I don't have a, let's go with condition. I guess a few of these code chunks I did not update based on choosing a different preset than I did. Wait. Oh, that's also. Did I assign region up here somewhere? Oh, I assigned it up here. So I was just looking for where so all of my code chunks down here are relying on a region column that I forgot to assign earlier. So here is where that region column is coming from that I just forgot to assign because I skipped these code chunks because we'd already talked about this. All right, so that's where that region column is coming from. So if I come back down here, change that back to region. So there are those two region. So there's the TIC for those two different regions of mass ranges. Any questions so far? All right, and the last thing before lunch, I'll just mention again, So by default, data in Cardinal is not loaded into memory until it is actually needed. So here right now, so far, we've actually been working with out-of-memory data. So when we plot those images, when we plot those spectra, all of that data is just loaded into memory on demand. If we do want to pull something into memory, so if we have an MS imaging experiment and a matrix of intensities such as this, and we've already imported the data, we can use the as.matrix coercion to turn that into a matrix and just pull that into memory as a regular R matrix. Or when we are originally reading it in, remember, we can set memory equals true if we want to load the data into memory when we first load it. The last thing I'll mention here is if you do need to convert directly between MS imaging experiment and MS imaging arrays, there are coercion functions to do that. So you can use as to convert between those two. There are also convert. These are internally calling these two functions for converting back and forth between them. Note when going in the direction from MS imaging arrays to MS imaging experiment, because we need all of the spectra to have the same MZ values. That does require choosing a single set of MZ values to represent as the bins for the MS imaging experiment. So if we're going from MS imaging arrays to MS imaging experiment, that does require binning the MZ values. Using this function, we'll try to guess appropriate bins for you. You can give it some additional information to use to guess those, but that is something that has to happen if converting from MS imaging arrays to MS imaging experiment. Going the other way is simpler. Yeah. But usually the way that we would go back and forth between those is through actually pre-processing the data. And then the output of that, the centroided data, will typically be an MS imaging experiment object. So after lunch, we will come back and cover pre-processing and then some statistical methods. Any questions before we stop here for lunch? All right, so that'll be it for now. We'll go ahead and take a break for lunch. We'll come back in, I believe, an hour at 1:30, and we'll talk about pre-processing the data, so how to pre-process the data, and then we'll talk about some statistical methods in the afternoon, and then we'll finish up talking about some future directions that we're working on. All right, so go ahead and get lunch now. If you ordered and paid, it should be waiting for you or arriving soon. Otherwise, you're on your own and free to go wherever you would like. But we'll come back here and start again at 1:30. Okay, let's go ahead and continue. So first, are there any questions or anything we need to get caught up on, or anyone think of anything over lunch break that you want me to need me to answer before we continue? Yeah. Sure. The question is on the scale option when plotting images. Go back up a little bit. Actually, for this purpose, let me actually. All right, so I'm going to go ahead and load a real example data set. Just to, oops. All right, so here, for example, we'll talk more about this data set in a bit, but just to answer the question on the scale option with an image, So we have kind of three image processing options available to us when plotting images. And those are going to be here, contrast enhancement, smoothing, and scaling. So each of these serves a slightly different purpose. So let me actually quickly go through each of these again with some real data. So mass spec images are often relatively noisy, and so contrast enhancement and smoothing can help with that noise sometimes. So for example, here, let me add a bilateral smoothing filter to this. So that just smooths out some of the noise. If there are still some hot spots that are especially bright and making it difficult to see the rest of the image, we can use contrast enhancement to further enhance the contrast. So here I used histogram equalization to do that. And then if we're plotting multiple images, let me just something. It's interesting. So here, for example, I have two images, one at MZ888, one at MZ889. And you'll see that the left image in general has a wider intensity range and higher intensity values than the one on the right. So it's going to appear brighter in certain places. And that can be fine if we're kind of looking to compare images and their relative abundance. So if we want to know that there's more of whatever 888 is in the left in this area than whatever 889 is over here. That can be helpful. But sometimes we actually kind of just want to compare the spatial patterns rather than the absolute intensities. And so for that, the scale option can be useful. And so what that does is it just scales the intensity ranges for the different image slices so that they have the same intensity range. So it scales them to as a proportion of the maximum intensity in each image, which is why you'll also see the color bar on the right at a percentage, and this will become from 0 out of 100% of whatever the maximum intensity is for each individual image. So that can be helpful for comparing spatial patterns between different images with very differing intensity ranges. Any other questions so far? It is. We haven't gotten to it yet, though. Yeah. So we'll come back to this one in a little bit. So before we get to that one, I want to go over some of the pre-processing methods. And we will again go back to our simulated data for a little bit just to more easily show some of the different pre-processing methods. So I'm going to be, let me plot. So we're going to go back to this simulated data that had just the rectangles and the circles, and then we'll move on shortly to working on that real data set. So for pre-processing, we have several different steps and a few different kind of categories generally for pre-processing. So in general, we are going to want to pre-process our data before we do any kind of statistical analysis, machine learning, anything like that. So some of the main goals of pre-processing are firstly to reduce the data set, the dimensionality of the data set. So rather than several thousand, 10,000, 100,000 potential MZ values, we have a smaller set of peaks that correspond to the analytes of interest. So in order to get from that profile spectra representation to centroided spectra, we need to do spectral processing and peak processing. So the spectral processing that we're just going to describe here is applied independently to each individual spectrum. So this is going to include things like normalization, smoothing, baseline reduction, recalibration of the MZ values, and the actual peak detection. And then once we get to actual peak detection, then we have a couple of ways of processing those peaks and getting to the final centroided version of the data set. So I'm going to start off by looking at the spectral processing, and then we'll move on to peak processing. So one of the first steps, either one of the first steps or one of the last steps that we typically do is going to be normalization. So one of the most important things that we need to do is to make sure that the different mass spectra across our data set are actually comparable to each other. And if we are doing this in kind of an unsupervised manner, so if we don't have any kind of reference proteins or lipids or any kind of reference analytes that we've put into the data that we know are some expected concentration, then we can rely on either total ion current TIC normalization or root mean squared RMS normalization. These two work just based on the intensities in every spectrum individually. If we do have some known reference features, so if there was a particular protein or something like that that we put in the data set that has an expected concentration, then we can use the reference method. But in a lot of cases, we don't have that. So by default, the thing we would typically do if we don't have any reference is just TIC, total ion current normalization. That's the general practice. RMS is another option that is similar to TIC, but just uses the root mean squared instead of the total ion current. So both of those are pretty straightforward. You can just call normalize and specify the method here. So before we move on to talking about other spectral processing steps, the general pattern for how Cardinal performs spectral processing is that the individual spectral processing steps are queued up and then are not actually applied until we want to apply all of them at once. So that is specifically for any of these spectral processing steps that apply individually to each mass spectrum independently. So normalization, smoothing, baseline reduction, recalibration, and the actual peak detection stage of processing peaks, all of these are going to be queued and then not actually applied to the data until we want them to be. So for example, come over here. So I'm going to be working with this simulated MS imaging arrays data set. So it's possible that you might be processing an MS imaging experiment object if you imported that from continuous IMZML. But a lot of times that will be, especially with high resolution data sets, the raw profile spectra will often be stored in the processed IMZML format, which will typically get imported as an MS imaging arrays object like this. So we're going to process this until we get to a centroided data set. So first I'm going to apply normalization. You can see that this prints out a message that we've queued intensity normalization right now. None of that has actually been applied yet. If I print out the data set again, you can see that there's a processing data slot that is the queued pre-processing. So intensity normalization was queued here. It'll also give me some notes, reminders about some of the things that I can do with this data set that has queued processing on it. So if I want to apply the processing, I can use the process function to execute any queued processing steps and return the result. If I want to just remove that processing, there is a reset function that just drops any queued pre-processing steps. And then the plot method will also preview any queued pre-processing, which isn't going to be that interesting with normalization because it's just scaling the intensities. All right, so we've queued normalization. We're not going to talk too much more about it because normalization is essentially just scaling the intensity so that they're comparable across spectra. Yes. So the question is on what are these actual methods, like what is total ion current? So let me again load up. Oh yeah, I've already queued some preprocessing. Um, so All right, so the question is on total ion current. So what total ion current means is the area under the curve of the entire signal. So basically, if I just integrated the entire signal here, the way that we typically calculate it is just to keep things computationally simple. And since is just to sum up all of the intensities here. So we're just summing up all of the intensities to approximate the area under the curve here. So that's total ion current is just summing up the area under the curve, essentially. RMS, root mean squared, that's the same idea, but just taking the square root of the mean squares of all of the intensities in the spectrum. And so what the normalization is doing here is really just rescaling so that all of the mass spectra have the same total ion current or the same root mean squared. So internally, these are implemented using the rescale function in matter. So rescale RMS is just going to rescale the root mean squared of a signal. Sum is what the TIC normalization is doing, so just scaling signals so that their total sum is the same value. And then ref, this is the reference normalization, which will just scale all the spectra so whatever reference feature we are giving to it has the same intensity in every spectrum. Yes, so the reason that TIC is kind of the default here is, well, firstly, we don't usually have a reference, and so we often need to use some sort of unsupervised normalization method. And yes, the assumption is essentially that for every mass spectrum, we're collecting roughly the same amount of actual ions, just in different abundances. And so we're basically normalizing every mass spectrum so they represent basically the same total number of ions per mass spectrum. So that's what essentially normalizing TIC is based on. It's based on the idea that each mass spectrum represents essentially the same total number of ions, and the actual intensities are their relative abundances to each other. Okay, so far we have queued normalization. So next thing is spectral smoothing. So we have the option of smoothing the mass spectra. Now, whether or not that's necessary is going to depend on your particular mass spectra. So let me, for example, zoom in on this a bit. So this mass spectrum would probably benefit from some smoothing. You can see there's a decent amount of noise there. So smoothing can be helpful during both peak detection and baseline reduction, as well as any mass recalibration that we decide to do. Just because smoothing, essentially the idea is to remove some of the noise in the signal. And so it's going to hopefully make any other processing, any other spectral processing we do a little bit more accurate and a little bit less affected by the noise. So here I have a couple of different smoothing options that I can plot together. Let me just plot these one at a time, though. So with a small plotting window. I'm trying to, oh, is that not? Okay. Guess that's not. Okay, so well, because the plotting method is a little bit unique for when we are previewing pre-processing, I guess it's not obeying some of my commands. So the key argument is getting ignored here. So that's something for me to look into further, but it is expected that the plot method is going to work a little bit differently when we're previewing pre-processing here. So we can see here is the original signal in blue, the smooth signal in orange. So what I'm doing here is I can use the smooth method to apply different kinds of smoothing. So we have a bunch of different smoothing algorithms. So here I'm specifying Gaussian smoothing. So this is the result of Gaussian smoothing. Here I can show Savitsky-Golay smoothing. A lot of these are going to look relatively similar. So Gaussian here is smoothing a little bit more than Savitsky-Golay. Let's see. So I have all of the different options listed here. So you can try different options and see which tends to work best for your mass spectra. Gaussian smoothing is, again, the most straightforward, but it can potentially over smooth a little bit and reduce the overall intensities of the peaks because it doesn't try to adapt for any local peak shapes or anything like that. The bilateral and adaptive methods, these both perform a kind of bilateral filtering, which will, just like with images, in images, it tries to preserve edges more. Here, the idea would be try to preserve the heights of peaks a little bit better. Diff is for nonlinear diffusion. Guide is for guided filtering. Another useful one here is PAG. So this is called peak-aware guided filtering. That's what the PAG stands for. And so this uses guided filtering, which is a kind of filter from signal processing, but tries to preserve the peaks better than a regular guided filter. Savitsky-Golay, which is a fairly standard smoothing technique in signal processing and mass spectrometry. We also have a very basic moving average filter as an option as well. So let me show you a couple more of these. So here's a bilateral smoothing. Oh, that one wasn't. Maybe I don't have bilateral as a distinct option here, just adaptive. Okay. Looks like it's just adaptive. So you can compare. So I expect this one. Yeah, so you can see with this is the adaptive filtering. It's going to preserve the heights of those peaks a little bit more than the Gaussian smoothing, which we have here. Let me try PAG. So this is going to be the peak-aware guided filtering. You can see that one preserves the heights of peaks even better. So I think the PAG one is often a good option in a lot of cases. Whether or not you need smoothing at all is going to depend on your data set. A lot of modern high resolution mass spectra don't even necessarily need smoothing much, if at all. But these are options available to you. And PAG, for example, this peak-aware guided filter is a new option that we have in the latest version. So let me go ahead and apply some smoothing. I'm just going to use some standard Gaussian smoothing. So you can see whenever I queue a new pre-processing step, it's going to list all of the queued pre-processing steps so far. So right now I have intensity normalization and smoothing both queued for my data set. Any questions so far? All right. Next thing is going to be baseline reduction. So if you have a data set that has a baseline, then removing that baseline is certainly going to be an important step of pre-processing so that you don't have that baseline as part of the actual peak heights or peak areas when it comes time to summarize the peaks in the data set. So we have three or four. Let me check. Yeah, so we have four different baseline reduction methods. One is called loc-min. This is a simple method that just relies on interpolating between local minima. So basically, we just go through the signal, find all the local minima, interpolate lines between those, and treat that as the baseline, and then subtract that off. Hull is for convex Hull estimation. So essentially, it's trying to find a bounding box on either the top part of the signal or the lower part of the signal. So the convex Hull method is just going to basically find a bounding box on the bottom of the signal and then treat that as the baseline and subtract it off. SNP, this is sensitive nonlinear iterative peak clipping. So this is a relatively standard baseline reduction method. There's papers on it that you can look up. I won't go into exactly how it works. And then lastly, median, and this just estimates the baseline from running medians. So basically a sliding window calculating the medians at each point. So for baseline reduction, all of these work fairly well. It just depends on what seems to work the best for your data. But in general, the baseline reduction is often pretty straightforward if you need it at all. So I'll go ahead and cue baseline reduction there. So far we have normalization, smoothing, and baseline reduction all queued up. Any questions on that? All right, so for this next step, I'm going to talk a little bit about mass recalibration. So this is a pre-processing step that, again, is optional. You may or may not need it depending on your data. So the purpose of the recalibrate step, also this is a renaming of a function called MZ-align in the older versions of Cardinal, but they're performing the same thing, which is mass recalibration. So you can certainly have some amount of mass drift or error in exactly where peaks are being measured. So here, for example, is some simulated mass spectra that are quite unaligned. So we have a good amount, a very visible amount of mass drift. This is more than you would probably see in real life, at least at the at this resolution, but just to show you how it works. So here, the idea is that we want to align this data so that the centers of the peaks and the shapes of the peaks are basically closer to right on top of each other, so that when we do peak detection and align those peaks, they are a lot closer together. So we want to go from this to this, where if I show you both of those, hopefully you can see that in the second version, we've aligned the data much more closely so that those peaks all line up together. So that's what the recalibrate function does. And I'm going to simulate some different data here that has a much larger amount of error in or mass drift in this. Again, I'm simulating a much more than you would probably see in real life just to make sure it's clearly visible. So there we're plotting that. So for recalibrate, you need to give it a reference, a list of reference peaks. So these are going to be the locations of peaks that we want to use for alignment. If you kind of similar to normalization before, if you have some peaks that you expect to appear in the data set, for recalibration, these do not need to be references that we expect to have a known concentration across the data set. These just have to be peaks that we expect to show up in most of the mass spectra in the data set, not necessarily all, but many of them. So here, if you don't happen to have that already, you can use the estimate reference peaks function to generate a list of reference peaks. The default of what this function does is just to calculate the mean spectrum and then perform peak picking on the mean spectrum. So you can see for this data set, it gives me a list of 9 peaks that I can use as my reference to recalibrate. There is a tolerance here. The tolerance here indicates how much we want to allow the masses to shift in either direction. So again, here I've made the mass error pretty large. So I'm giving a pretty large tolerance that will account for that. So what the tolerance is representing exactly is, again, exactly how much we want to allow the signal to move in either direction. You want to set a tolerance that is large enough that we can actually move it to the proper peak locations, but is also small enough that we're small enough so that we're matching peaks to the correct peaks. Peaks in the individual spectra to the reference peaks. If you set this too large, then we might be shifting things too much. If you set it too small, we might not be aligning things to the correct peaks. So it can be a little bit tricky to play around with that until you find something that produces good results for your data set. So let me go ahead and run that. And then at the end of that, we can see those peaks were fairly nicely aligned. Again, this is something that might not be necessary for you. And a lot of times it's often not necessary if the instrument is already fairly well calibrated. But when it is necessary, this function will hopefully help. Yeah.
So when I preprocess, I generally set the tolerance to half the estimated resolution of mass resolution of the data.
Are you talking about when you import it, or?
Yeah, when I do MZLI or
Okay. Okay.
So is that a good default to go by, or
I mean, that's probably you said it to half the resolution. That's going to be too small to actually do anything,
Yeah.
most likely. Which, like I said, it's not often a necessary step, so that might be fine in a lot of cases. Unless I know that a data set isn't going to need recalibration, this isn't a step that I would typically do, unless I already know that it's a potential issue for that particular data set. Yeah.
The best way of see if it needs treatment.
Yeah, pretty much. Yeah. 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 So essentially, this is something where you plot the data and see if it looks like your peaks are drifting a bit too much. And it's both not always necessary because a lot of data, if the instrument was reasonably well calibrated, you won't need this in the first place. And then also the peaks themselves are going to be aligned later on. So in the process of processing the peaks, we're already going to be accounting for some amount of error. This is just an extra step to do before that if we want to try to make that easier for the peak processing later on. So we have 3 methods for this. This is one of those methods that I haven't tested extensively, again, mostly just because we only have so much data that actually requires this. The LOCMAX method just uses a well, technically a novel local regression technique to shift the spectra. So this is our own method that we have been trying to use for this. It seems our collaborator Melanie says that it works well, good for her data. So I can just take her word for it on that. But beyond that, I haven't tested it too extensively. So this is one of those methods where if you do need it and if you want us to improve it, share some data and we can look into doing that. We have 2 other methods. Again, I haven't tested these extensively on mass spectra data specifically, but these 2 other methods are very very well-established methods in signal processing more generally. So dynamic time warping and correlation optimized warping, these are both standard signal alignment methods. All right, and then now to get to the peak processing itself, let me just plot a mass spectrum again here. So actually, let me go ahead and apply all that processing. So what you saw just now, actually, maybe I'll go back and do that again real quick, just so I can describe what I'm doing before I do that. All right, so I'm going back, queuing up normalization, queuing smoothing, queuing baseline reduction. I'm going to skip recalibration because this data set doesn't need it. All right, so far we have intensity normalization, smoothing, and baseline reduction all queued up. At this point, I'm going to go ahead and apply those, and then we will talk about peak picking. So to process queued processing steps, you can just use the process function. So that will automatically apply all of pre-processing and return a new data set with that pre-processing done. So I'm going to assign that to MSA pre here. So now we can go ahead and do some peak picking on this data set. So we still have an MS imaging arrays data set, so nothing has changed other than we now have a version that has been processed in terms of normalization, smoothing, and baseline reduction happening. So now we're at the stage where we're going to do some peak picking. So we have the peak pick function for performing peak detection. We have a number of different peak detection methods. So I'm just going to walk through them here real quick. So I'll note that first off that one of these names has changed from the previous version. So what was called MAD in the previous version of Cardinal is now called DIFF, DIFF. It is still currently the default. So if you're not setting the method directly, then the default should still be essentially the same. I renamed it just because it makes more sense for what the method actually does. So what these different peak detection methods do is all of these except for the last one here. So the first 5 of these all start off by finding local maxima in the spectrum. So local maxima are detected just by using a sliding window approach. So we basically slide a window of 5 or so data points across the entire spectrum. And whenever we have an intensity that is larger than all of the neighboring data points around it, we're going to consider that a local maxima. We're going to have way more local maxima than actual peaks because of the noise. So that's the first step, is detecting local maxima. And then the part where these methods differ is in how they estimate the noise. So each of these is going to estimate the noise in a slightly different way. So the diff method, again, this is previously called the MAD or MAD method. It's now called diff. This one estimates the noise based on the mean absolute deviations between the spectrum signal itself and a rolling average of its derivative. So it's basically taking the idea that the derivative of the signal, so basically the differences between consecutive intensities in the signal, that derivative is going to be dominated largely by the amount of noise in the signal. So we can use the deviation between the signal itself and its derivative to kind of estimate the amount of noise, the noise level in the signal. So that's what diff does. That is the default. It seems to work relatively well across a relatively wide range of data sets. So that's the reason I've chosen it to be the default. But some other methods might work better for different data sets. The next two, SD and MAD, MAD, Both of these estimate the noise from the standard deviation or the mean absolute deviation of the spectrum after convolving that spectrum with a wavelet. So essentially, that's just so that's something that's borrowed from the continuous wavelet transform method down here. But that's the same way that continuous wavelet transform estimates noise is just taking either the standard deviation, mean absolute deviation, or a quantile of the spectrum after convolving it with a wavelet. So that's those are two other ways of estimating the noise here. The quantile method estimates the noise from a rolling quantile of the difference between the original spectrum and a smoothed version of the spectrum. So what the quantile method does is it takes the original spectrum, applies one iteration of anisotropic diffusion smoothing. So it's just a smoothing method. And then looks at the difference between that original spectrum and the smooth spectrum. We can expect the difference between the original noisy spectrum and a smoother version of that spectrum to be mostly the noise. And so then we just take a quantile of that noise. You can specify the quantile explicitly. Let me see what the default is. Oh, wait, no, it's the default being the 95th percentile of the noise. So that's quantile. The filter method. So this one's kind of unique. This is actually a noise estimation algorithm that works even if the data has already been peak picked. So this comes from a paper called Dynamic Filtering to Estimate Noise. And so what this one does is it basically assumes that each spectrum will have at least one peak that is noise. Each spectrum will have at least one noise peak. And so this filtering method assumes that the lowest intensity peak in every spectrum is noise. And then it tries to separate the peaks into a group that is signal and a group that is noise. And it just does that by looking at the next most intense peak, the next most intense peak, until it can kind of find a separation between noise peaks and signal peaks. So that's those five. They all work relatively similarly. They start by looking at local maxima, and then they calculate the noise and report peaks based on a signal to noise threshold that we can select. The last one of these is quite different. Continuous wavelet transform. We can still specify a signal to noise ratio, but this one works a bit differently. It works by convolving the signal with a wavelet at different scales, finding what are called ridge lines across different scales from that wavelet, and then using those ridge lines to figure out the peaks. It's a somewhat popular peak picking method in traditional mass spectrometry. It's sometimes considered one of the best methods. I haven't actually found it to be that robust in practice. There's a lot of it can be a really useful method, but you do have to play with the parameters a bit to make sure that it's working appropriately for your data set. It is also quite slow. I wanted to make sure that I wanted to add this implementation just as a kind of a reference point, because it is a commonly used peak detection method. But I will say that if you use this one, it is going to be a good bit slower than the rest of them, just because it is a more complex process of finding peaks. So let me go back over here. So here's the default method. So here I'm doing peak detection on my smoothed baseline reduced spectra using the diff method. So this is using the derivative of the signal to calculate the noise. I'm using a signal to noise threshold of 3. So the height of the peak has to be at least 3 times as large as the estimated noise. And so we can see this does a pretty decent job. We certainly have some what are probably false positives with some low abundance peaks down here. But it's also possible that those might be real peaks. Here is the filter method. You can see this one much more aggressively filters out those low intensity peaks for this particular data set. And is probably a little bit closer to what the actual peaks are for this simulated data. So the best method for peak detection is really going to depend on your data set. So this is, again, one of those areas where I would preview the different a few different peak picking methods, usually zoomed in on a region of the spectrum so you can actually see the peaks and see what's going on, and just see which one tends to be doing a better job. So I'm going to go ahead and queue up the filter method for peak detection here. All right, so we've queued up peak picking here. I guess a couple other options I'll note from peak detection. So signal to noise ratio is one of the options to be aware of. That's why you set your signal to noise ratio threshold for labeling something a peak. The other argument here is whether the peak should be summarized by its height or its area. So the default is height, which is just going to take the maximum height of the peak to summarize as its value. The other option is area, in which case we'll start from the center of the peak, find the local minima, the closest local minima to that peak, and then integrate under the peak to those local minima, and return that as the area. All right, so the tolerance here is only used if you pass a reference here. So the peak picking here, this can also be used to summarize peaks according to a reference. So in the previous versions of Cardinal, there is a peak bin function that has now been folded into the peak pick method. So if you want to just summarize peaks from a data set based on a list of reference peaks, you can just use peak pick to do that and pass a reference of MZ values for the reference peaks. All right, so far we have talked about the spectral processing. Now let's go ahead and focus on the peak processing. So we've decided on a peak, we've queued up a peak picking method. The next thing to do is to align those peaks. So I haven't actually applied that peak picking method, but when I do, the next thing to do will be to actually align those detected peaks, because what will usually happen is we'll find the same peaks in very slightly different locations in every mass spectrum. So we might find the same peak at 500 MZ or 500.01 MZ, 499.99 MZ, and we want to align those because those are probably going to be referring to the same actual peak, the same actual molecule. So peak alignment will automatically, if I call peak align to do peak alignment, this will also automatically apply any previously queued pre-processing steps. This is another new default. Previously, you still had to call the process function to apply all the pre-processing. Now the last step in processing, which is usually processing the peaks, will automatically do that for you. So you often don't have to separately call the process function to apply the pre-processing. So I can just pass in this data set with queued peak picking directly to peak align. Peak align will both apply that peak picking and then also align the peaks. I need to set a tolerance for the peak alignment. So this is essentially the largest expected gap between peaks, essentially. So any peaks that are closer together than this tolerance, which again, you can set the units as either parts per million or absolute MZ values. Any peaks that are closer together than this tolerance will often be merged together into one peak. We use a little bit more rules than that. So if they have a pattern that makes it look like these are really different peaks, they will be kept separate in some cases. But if that is not the case, then peaks with that are closer together than this tolerance will be merged into the same peak. So let me run all of that. So you'll see first off, we're applying the peak picking to each spectrum. And then we are doing the peak alignment. And so we align to, ultimately we had 4,408 reference peaks across the whole data set, which is more peaks than we probably actually need. So one thing that you can check after that peak alignment is done is in the featured data of the data set that is returned from that. I'll also note that an MS imaging experiment is returned from that. We started off with an MS imaging arrays object. After peak alignment, that returns an MS imaging experiment object. So all of the spectra have been aligned to share the same MZ values. Now, a lot of those mass features are probably not real peaks that we might still want to drop based on how often they appeared in the data set. So the featured data after peak alignment will have two columns for the count and frequency of the peaks. The count is just how often that peak was observed in the data. The frequency is just the proportion of how often that peak was observed. So we might want to further do a subset features at this point and drop some peaks that do not occur very often. So that's the next thing we have here. So dropping peaks with frequencies, or keeping only the peaks with frequencies in more than 10% of the data set in this example. So after that, here we end up with 35 peaks, which is a lot more reasonable than the 4,000 that we started with. Yes. No. So the question is peak align calling recalibrate in the background, or if there's a relationship between those two? So no, peak align and recalibrate have really no relationship to each other, and they do not work in the same way. So recalibrate works on the entire spectrum itself. So it takes in the raw intensity, the intensities for the entire spectrum. And recalibrate assumes we're looking at an entire profile spectrum and is trying to shift or warp that entire signal. Whereas peak align, all peak align is doing is it's going to look at the MZ values of the peaks that are returned from the peak detection. So the specific input to peak align is just going to be the list of the peaks. So the list of the MZ values where the peaks were found. And then what happens with peak align is it creates a bunch of MZ bins that span the entire MZ range and have a resolution smaller than the has enough. It creates a bunch of MZ bins, enough bins to fill the entire mass range, and enough that they are smaller than the given tolerance here. It bins together the peaks into those bins, counting up how often a peak was put into one of those MZ bins. And then any bins that are closer together or similar to that tolerance are going to be merged together. One of the additional rules is that we look at the counts of the peaks. If it looks like we have a kind of local minima in the count, that means that we're probably going to another distinct peak. And so if that happens, but we're still within the tolerance, then we're still going to keep those as separate peaks. So that's one of the additional rules that goes into this. So that's what's happening with peak align is it's generating a bunch of MZ bins. It's going through all of the observed peaks, putting those into the bins, counting up how often they appear in each of them, getting the average MZ value. So the output, the MZ values here, these are not the MZ values that the bin started with. These are the average masses of the peaks in each bin. Any more questions on peak align here? Yes.
It is better to retain some rare peaks. Is it better to have a higher SNR value or to subset of like if you have too many?
So the question is on what is kind of the better practice if we are trying to retain peaks that are relatively rare in the data set. So we'll get into a little bit more of that because that also relates to one of the things we'll talk about here in a moment, which is the peak process function. So let's see, I think yeah, so that's it on peak align specifically. So here I'm plotting the peaks here. So once we have a data set that is centroided, so I'll note, so the output from all of that is a centroided data set. So centroided is true because this consists now only of centroided peaks, and we filtered it down to just 35 peaks. And because I simulated this data, I know that's pretty close to the actual number of peaks. All right, so okay, so before we talk about the peak process function, I mentioned that you can use peak pick based on a reference. So here is an example of that. So here I'm taking the MZ values from the peak picking that I just performed. So say that I have this list of MZ values where I expect peaks to be, or these are the peaks of interest. I can just use those to directly summarize my non-centroided data set. So here is my the data set that I have that was processed with normalization, smoothing, and baseline reduction, but no peak picking yet. And so I can use peak pick on this data set, pass those MZ values as the reference to the ref argument. I can specify a type still, so I can choose height or area. And then in this case, for peak pick, I do need to pass a tolerance. You might have noticed that tolerance argued in peak pick before. This one is only used if we specify a reference. So this tolerance has nothing to do with the peak detection unless we specify the reference. So then what this tolerance is it's just measuring how close a local maximum has to be to one of these peaks for it to be considered one of these peaks. So we just find the local maxima in the spectra, match them to these peaks, and then summarize it using either height or area as described before. So I can queue that up. I can apply that as well. So if I already know what peaks or their MZ values that I want, I can use peak pick to just summarize those. All right, so the last or second to last thing in processing I want to talk about here is the peak process function. So this is a new function that we're introducing in Cardinal version 3.6 to make all of the peak detection, peak processing easier. So the normal process that we were doing just before now is separately using peak pick to do the peak detection, and then peak align to align those peaks. And then optionally, we can also peak pick based on a reference or summarize peaks based on a reference. So peak process wraps all of those different steps up together with a couple of different kind of general peak processing workflows that it can perform. So let me jump back over here to describe those. Here we are. All right, so peak process kind of has two general pathways that it can go down. One of the pathways for peak process is that it just does peak picking on every spectrum, and then it aligns all of those peaks together, and that is your centroided data set. The other thing that peak process can do is to optionally perform peak picking in a subset of the data set, use that subset to generate a list of reference MZ values of peaks, and then summarize those peaks in the entire data set. So those are the kind of two main workflows that peak process supports. If you do not set this sample size option, then it will just do individual peak picking on each individual spectrum, align those, and produce the centroided data set. If you do set this sample size option, it will perform peak picking on a subset of the data set. It will use that subset to generate reference peaks, and then it will go back and summarize those peaks in the entire data set for every spectrum. So the reason that we have these two possible approaches are because they offer slightly different advantages and disadvantages in terms of how often we might find or miss peaks, both based on their intensities and based on how rare or common they are in the data set as a whole. So if we have a more rare peak, for example, that only occurs in a small part of the data set, we might not necessarily see that peak really show up if we only do peak picking on a subset of the data. So that's one reason to potentially perform peak picking on the entire data set for each spectrum individually. But on the other hand, the kind of downside of doing peak detection on each individual spectrum is that peaks that are relatively low intensity have a higher chance of potentially being missed if the data is still a bit noisy. So if we are just doing peak detection on each spectrum individually, then if we don't detect a peak in a particular spectrum, it's just going to be missing for that spectrum. We can potentially go back and impute it later if we do imputation, but unless we think of to do that, which is not currently directly supported, although you could do that, but it's not currently one of the out-of-the-box features that we have, that peak might just be missing. So that is where performing peak picking on a sample and then summarizing those peaks for the whole data set might give you an advantage if you have these low intensity peaks, because they don't need to show up in every spectrum. They just need to show up in enough spectra that are part of the sample. And then when we go back and summarize those peaks in every mass spectrum, even if the peak isn't intense enough that it would get selected as a peak on its own, we're still going to summarize it because we're summarizing the data set based on those reference peaks. So that's kind of the trade-off here is we're kind of, if we're peak picking on a sample, then usually the centrated data from that will have fewer missing peaks and will be a little bit more complete. But we could certainly potentially miss out on more rare peaks that only occur in a small part of the data set. Versus on the other hand, we could do peak picking on every spectrum and then know that those rare peaks should be captured in the spectra that do have them. But we might have more missing data in general in that case. So those are the kind of two general trade-offs we have with peak process. And those are both processes that we supported before and we tried to describe in our teaching materials before, but now there is a function that just basically does either of those two things, just depending on whether you set a single argument or not. So if you don't set sample size, this is just going to do peak picking on everything and then align everything. If you do set sample size, this will peak pick on a subset of the data and then align those and then extract those peaks from every spectrum. The one other argument here that is different is there is an argument for the filter frequency. So this just is performing the same step that we previously performed manually with the subset features that we did up here. So peak process here just serves to streamline all of the different peak processing steps, including the actual peak detection. So you can specify the peak detection methods, signal to noise ratio threshold, what kind of peaks. You can specify the tolerance for the alignment, sample size for how large, for how many peaks we want to look at first in the subset, and the filter frequency. Both of these can take either a proportion or a count. It will figure that out just based on whether the value you give it is less than or greater than 1. So sample size, this could be the actual size of the sample or the proportion of the data to use. Same for filter frequency. The default for filter frequency, since you see that this is just set to true, you can set this to an actual number. If it is just set to true, it will just remove peaks that were observed only once. So I'm going to apply peak process here. So I'm going to do peak picking on 30% of the spectra to create a reference that will then be used to summarize the whole data set. And my filter frequency is 0.02. So peaks have to appear in at least 2% of that sample to be used. And so I can run all of that. And I get the result, this time with 83 features, which is more than I need, more than they're actually in the data set, but still good enough. Better to have slightly more peaks than a bit too few. All right, any questions on any of the peak processing that we've done? All right, yes. How is it calculating the signal to noise ratio? So that is just going to be based on how the noise is estimated. So the most of the different peak detection functions here are differentiated just based on how they estimate the noise, as we were talking about. So this describes how the noise is being estimated for each of these. And then the signal to noise ratio is just going to be the intensity of the peak divided by the estimated noise. So signal to noise ratio of 2 means that the height of the peak is twice the noise. Uh, for estimating the noise or the Okay, so the question is on for estimating the noise, do we use kind of a window or how is the noise estimated a little bit more specifically? So if you want to see further documentation on how the noise is estimated, so the actual low-level signal processing function that does that is in Matter. So there are these different est noise functions in Matter that do the actual noise estimation. If you want to see the actual noise levels that they estimate. And you can see several of these do take an N bins option. So there is the option for several of these, not all of them, but for several of these to have a changing noise level for different areas of the mass spectrum. The default for some of these is to have just a single noise level for the entire mass spectrum, but for some of them you can change the number of bins that the spectrum is being split up into. So for example, the default here, this is the default noise estimation function, which defaults to 1 bin. So 1 noise level for the whole spectrum, but you could pass in more bins to that, in which case we would have different noise levels for different parts of the mass spectrum. So each of these works slightly differently. You can read the documentation for the arguments here. So quantile, for example, this is a rolling quantile, so this will be different for different parts of the mass spectrum always. And here, this is the size of the slide-in window for the rolling quantile. Similar for the SD and noise and MAD methods down here. All right. Any other questions so far? All right. So while we're on the process of applying all of this signal processing stuff, I think it's a good time to point out a few of the other options that are going to be common to a lot of the different methods in Cardinal generally. So there are 3 things here to pay attention to that are going to be common across a lot of the different Cardinal methods. These are the number of computing chunks. Actually, I guess verbosity you don't really have to pay much attention to, and then the BP param. So the way Cardinal works is it generally applies any sort of functionality or calculation in chunks of the data set. You can see how many chunks is used from get cardinal n chunks. The default is to split up the data into 20 chunks. As you can see, that's usually a fairly reasonable number for both for the trade-off between like speed and how much memory is being used. But you can certainly change that with set cardinal n chunks here. In general, the fewer chunks, the more memory is going to be used because each of those chunks is going to be a bit bigger. The more chunks, the less memory is going to be used because each of those chunks is going to be smaller. But the trade-off of that is also that fewer chunks will tend to be a bit faster because we're breaking the data into fewer pieces, but each piece will use more memory. So that's one thing you can set. Get cardinal verbose. So verbosity, this is just whether progress messages are printed or not. The default is true, but you could turn that off if you wanted. And then the last one here, this is get cardinal BP param. The default is null, but BP param, this is what specifies what kind of parallelization to use, if any. The default is not to use any parallelization. That's just for compatibility and to avoid any potential issues that might come up. Because once you do try to run things in parallel, that adds some additional complexities that can make things hard to debug and figure out if there are any issues. But this is another option that you can set. I won't go too much into the different options that are available right now. They are documented in the BioC parallel package. So you can just set different registered backends using the set cardinal BP param function here. So for example, if you are on Mac or Linux, then the most efficient one would be multi-core param on Mac or Linux. And that will run things in parallel, doing all of that. So you can see that took a little bit faster, or that was a little bit faster. On Windows, you would have to use the snow param option. So it's just a different parallel option. But the default, which I'll set it back to, is just null, which means no parallelization. The advantages to using parallelization, of course, is that potentially it could be faster. That's going to depend on the size of your data set and whether the additional overhead is really worth it or not. The backend that you use. So on Windows, unfortunately, SnowParam is just a bit slower. It's a bit more stable, but it is going to be slower than multi-core param on Mac or Linux. It just has a bit more overhead. But it does have the potential to be faster than running things serially, which is the default. When you run things in parallel, though, it will use more memory because we're starting additional R sessions and moving some of the data to those R sessions. So you do need more memory if you are running things in parallel. Not necessarily that much more if you are working with out-of-memory data. But especially if your data has been loaded into memory, that is going to use quite a bit more memory if you use parallelization. All right, and then the last preprocessing step I want to show here is binning. So most of the time, you probably won't need to call bin directly. But if you do want to bin a data set to either specific MZ values or to a specific mass resolution or something like that, you can just do that with the bin function. This is done kind of lazily, so no data is actually changed. It just basically returns a data set that whenever you access data from it will be binned at however you ask for it to be binned. So for example, here I have an MS imaging arrays and we have our 2048 spectra from this. Now suppose I want to bin this data to unit resolution. So one MZ width bin, MZ bins. So resolution equals 1, units equals MZ. If I don't specify a mass range, this will just use the mass range from the first mass spectrum in that data set. So you can see the result is returned right away. We binned the intensity from MZ396 to 2316 with an absolute resolution of 1. And if I print out the result, one thing you'll notice is binning it changed it from an MS imaging arrays object to an MS imaging experiment object. So this is another way to quickly go from an MS imaging arrays object to an MS imaging experiment object is just to bin it according to whatever resolution you would like. You can also pass in the mass range if you would like. So here we binned it to 1,921 mass features. So the other place where this might be useful is if you do have multiple data sets that you want to combine into a single data set, you can specify the mass range and the resolution, or specify even just specific MZ values. So you can take the MZ values from one of the data sets and just use that as a reference to bin the other data sets to the same MZ values. That will work as well. And then that would give you data sets that you could then combine. Any questions on binning? Okay. The last thing here before we switch over to some real data is exporting. So if you want to write an IMZML file, you can do that. So here I'm just creating a temporary name for my IMZML file. So this is the file name. You would, of course, use a file name that is sensible to you. You can use the write MSI data function to write an IMZML file. You can pass it a .imzml extension, and it will figure out you want an IMZML file. Much like reading in data, there is a separate function for writing IMZML and for writing analyzed data as well. So let me go ahead and write this file. Oops. Did I not? Oh, guess I need to run this up here. All right, so let me write this MS imaging experiment that I just made. So the defaulting cardinal for writing IMZML is designed to make it easy to make sure that you're transporting both the IMZML and the .ibd file together, in that it writes both of those to a single directory that actually has the directory itself has a .imzml extension, so you can find it pretty easily. Let me go ahead and show you what that looks like. All right, so firstly, here's a bunch of temporary files that I've been creating this R session. This is the folder that got written when I wrote that data set just now. You can see it has a .imzml extension. So that means if people don't know that IMZML is actually at least two separate files and they just want to move the folder, it'll be a little bit hopefully prevent mistakes in doing that. You can see when I open that up, I have the expected IBD and IMZML files. A new feature in the current version is also writing the pixel data and the feature data if there are more columns than the kind of defaults. So if there's just the pixel coordinates, we won't bother to write those. But if there are additional metadata columns, those will be written as well. And those are just written as tab delimited text files. So you can import them in something else if you wanted to. And then those are also re-imported if I use read MSI data. So read MSI data will look for other files, tab delimited files with the .f data and .p data extensions that we will use for the feature data and pixel data. So if I import that again, you can see that it recognized those files and included those. We got those columns in our pixel data and our feature data now. So that's a new feature in the new update is to make it easier to write metadata as well and read it back in. Okay, covered some of that. All right, so I'm gonna go ahead in the time that we have left before break. I'm going to start looking at some real data, and we'll continue looking at this after break. So I'm going to go ahead and go to the folder labeled 3, case study. I'm going to skip the workflows. These are just showing, actually, wait. No, actually, I am going to go to workflows first. Sorry about that. So I'm going to go to workflows, and I'm going to look at the segmentation, MSI segmentation R markdown from the workflows folder. I'll pull up the HTML as well. All right, so before we go to break, we're going to go ahead and start talking about some real data and some statistical methods. So here we're going to be taking a look at that pig fetus data set that we saw a little bit earlier. So this is going to be an example of an unsupervised analysis. So unsupervised meaning that we don't have any known class labels. We are not trying to perform classification into healthy and disease or anything like that. We're also not trying to do statistical testing. Instead, we're just kind of trying to find the different regions of this sample and kind of what molecules are distinguishing the different regions of our data. So this is data from a section of a pig fetus. This was collected by Livia back at Purdue in our Graham Cook's lab. So this is a pig fetus. We have the brain on the left-hand side. We have the liver. That big dark region is the liver. You can see some of the spine and back tissue. And then in the center there, the little thing in the center, we have the heart. So I'm going to go ahead and load this data set. So this data set, along with a couple others, we'll be looking at here. These are real data sets that are stored in the Cardinal workflows package. So they're actually originally stored in an old format. So I'm going to load them using this example MSI data function that will automatically put them into our new format for us. So example MSI data function from Cardinal workflows will return these example data sets in our current MS imaging experiment representation. So let me go now back over here to our studio. Go ahead and restart R. So I'm working from a fresh session. Load Cardinal. Any questions so far? How are we doing? Everything okay? Yeah. Good question. So the question is about binning and when we might want to do binning. So like I think I referenced earlier that in general, there's only a few circumstances in which you would actually need to call the bin function on your own. The main example of that being either you need an MS imaging experiment object from an MS imaging arrays object right now. That might be to plot an image or something, because that's not currently supported on MS imaging arrays. Or to get all of the data sets to have the same MZ values in order to combine them if one of them is an MS imaging experiment object. So those are really the only two main times you would want to bin directly like this. In general, whether you need to do that or not, or when you would need to do that, typically this is only something that you would do on profile spectra in the first place. Once you have centroided spectra, they're already summarized. They've already been reduced to peaks. There's no reason to bin at that point. I'm pretty sure bin will actually just fail if you try to do it on centroided. I think I checked that. I don't fully remember, but I think I do. So the two times that you would want to call it to say combine things are if you have at least one data set that is already an MS imaging experiment object, in which case you need all of the data sets to have the same MZ values in order to combine them. If you have MS imaging arrays objects and all your data set are MS imaging arrays, then you can just combine them because there's no shared MZ values. So you wouldn't need to bin them in that case anyway. So generally, I would not bother calling it before pre-processing unless you need to combine data sets or unless you need an MS imaging experiment object at some point. If you have MS imaging arrays, you can combine those without binning. I would process them without binning as well because that way you're processing the actual raw data rather than the binned format. Um, but yeah, so that's yeah. I you shouldn't need to use it for the most part outside of those two circumstances. Any other questions so far? All right, so just started a new fresh R session. I just loaded up Cardinal. Let me go ahead and get this pig 2 or 6 data set. So this is our pig fetus data set from Livia way back at Purdue in my PhD days. So this is a relatively small data set for these days standards, but was decently sized at the time. So we have 10,200 mass features, MZ values. We have 4,959 spectra. We have the data has already, I believe, been, whatchamacallit? Yeah, subset to include only the region with the actual pig. So if we've already removed all of the pixels except those that are in the pig's body, so we don't have any background pixels here really to worry about. You can see here that if I just plot the run, it'll just show me what my runs are and where my pixels are for that. So that's useful sometimes just to check the shape of an object if we have a non-rectangular data set. So we have just over 10,000 features. Our mass ranges is from 150 to 1,000. We have just under 5,000 spectra. So we're going to need to do some pre-processing on this data set. First, I can visualize a couple images. So this is the data set we were looking a little bit at before. So here, for example, I'm looking at the ion image for MZ885.5. In this one, we can see the liver there on the right. We can see the brain there on the far left. It's another good example of showing some of our image processing. So for example, here is a good example of guided smoothing, bilateral smoothing. You can see how those tend to preserve the edges better if you look closely at the, oops. What? Well, that is wild. That's, huh. That is strange. I have no idea what's going on with that. Something funny is going on there. Okay, so something funny is going on with that smoothing. I don't know what's up with the Gaussian smoothing there. Um, Everything else looks fine. All right, well, something is going on weird with that Gaussian smoothing. Take a look at some of the contrast enhancement options. So histogram equalization, you can see how that makes certain regions brighter, improves the contrast of the image. We can look at the adaptive version of contrast enhancement. You can see that actually is kind of bad for this particular image. So regular histogram equalization seems to work better for this image. The adaptive histogram equalization will try to adapt to different regions. And in this case, it looks like it's adapting a little bit too much to different regions. All right, so we've already cropped this so that we only have the pig tissue itself. We can do some pre-processing. So for example, let's go ahead and take a look at the mass spectrum so we have an idea of what this data set looks like. Yes. Let's go back here. Um, Sometimes guided will produce some missing pixels because of the way it's calculated. I don't know what's going on with the Gaussian one there. Yeah, everything else here looks fine. Sometimes some of the smoothing methods will freak out a little bit, for lack of a better term. It's usually the guided filtering, which is why it's really weird that Gaussian is the simplest one there is. I don't know why it's doing this. But yeah, the intensities there are really weird. Let's try a different. Huh. I don't remember this happening a moment ago. Let's try simulating something. Works fine there. All right, I don't know what's going on with that. I'll have to take a look. Sometimes, yeah. So yeah, I don't know what's going on with that smoothing method there. Every once in a while, some of the smoothing methods will look a little bit weird because they sometimes they just encounter things that they weren't necessarily designed to do. Especially part of it might be, and usually with the other methods like the guided filter, it's usually the case that it has to do with the missing pixels and when we have a non-rectangular image. So that I wonder if that might be what's going on, although Gaussian is simple enough that shouldn't make a difference. But certainly every once in a while, I need to look at exactly how the filter is handling the imputation of the surrounding pixels there. Um, but anyway, it is time for a break. So let's go ahead and take a break. So when we come back, we'll continue to work through some of the examples here with this data set. We probably won't get to some of our statistical methods, but we can kind of figure out what exactly we want to spend our time on in the last session. And there's also some future directions, co-registration stuff. That size we'll be talking about depending on how much time we have. So that's another thing that we'll talk about. But we'll see how much of this statistical method stuff we can do with this data set when we get back. All right, so go ahead and start again. So we're in our last session for the day. So what we're going to do is I'm just going to go ahead and finish going through this workflow. And so we'll cover a little bit of statistical methods in this workflow. And then after however long that takes us, I'm going to go ahead and turn things over to Sai to talk a little bit about co-registration and multimodal experiments, which is part of our kind of our future roadmap in terms of things that we're looking forward to supporting more in the future and what our kind of ongoing work is. So we'll go ahead and finish this up, and then we'll switch over to that. And then after that, and any time we have left, we can go back over any topics you would like me to. If you need any personnel help working with anything or getting anything working, we can do that as well. All right, so we were looking at this pig fetus data set. So let's go ahead and summarize it so we can have an idea of what our mean spectrum looks like. So I went ahead and summarized our features here. So we can go ahead and plot our mean spectrum. So this is what our mean spectrum for this data set looks like. So we have a bunch of peaks here down between, say, 200 to 300 MZ. We have some tall peak over here around 500, a few more peaks over here around 500, and then a bunch more over here around 800 or 900. We can also go ahead and plot our TIC across this image. And so we can see that we certainly have variations in the total ion count for the different mass spectra in this data set. So in general, the liver seems to be more intense, as well as that kind of fatty back tissue. So we're going to normalize for total ion count as we continue here. So I'm going to go ahead and process this data set now. So just like we were already doing, I'm just going to take our PIG 206 data set. You'll notice one thing I'm doing here is I'm using this little pipe operator. So all this pipe operator does is it takes what is ever on the left-hand side of it and passes that as the first argument to the right-hand side of it. So for example, instead of this image, calling this image function like this, using the pipe, I could rearrange that to look like this. So the left-hand side of the pipe becomes the first argument to the function on the right-hand side. And so these two lines of code are actually doing the exact same thing. So this can be useful for chaining together different functions, especially in a pre-processing workflow. So here, just so you can recognize what's going on here, that's what this pipe operator is doing. I'm taking my PIG 206 variable, passing that into normalize, and then passing that into peak process. So not doing any smoothing or baseline reduction. This data set doesn't really have a baseline, and it's relatively clean enough that it doesn't really need smoothing either. So I'm going to go straight from normalization into peak processing. So you can see here, I'm setting a sample size of 0.1. So we're going to do peak picking on 10% of the data with a signal to noise ratio threshold of 3. And then for the peak alignment, I'm using 0.5 MZ as my tolerance because this is a relatively low mass resolution data set. It is over a decade old at this point, of course. So after that, we end up with a centroided data set with 687 peaks. So you can see that here. If I want to, I can take a look at what those peaks actually are. I can see those peaks here. Got 687 of them. All right, so let's go ahead and visualize a few specific ions here. So here we have 187.3. So this happens to be an ion that is relatively high abundance in the heart only. So we can see the heart right there in the center. We can visualize MZ840 here. So this appears to be more abundant in the brain and along the spine. And then lastly here we have 537, which seems to be more abundant in the liver. So those are kind of the three main morphological structures that we're going to be looking for in our analysis. So let's go ahead and apply some simple statistical methods. We're actually going to start off with just some unsupervised dimension reduction here. So I'm going to start off with PCA, principal components analysis. So principal components analysis is a dimension reduction technique where basically we are trying to reduce the data set to a smaller number of features or dimensions that capture as much of the variation in the data as possible. So rather than how many do we have? We have 687 peaks. So rather than our 687 peaks, what PCA does is it tries to summarize as much of the data set as possible in only a few components. So I'm going to ask for 3 principal components specifically. So I'll go ahead and run that. You can see that runs pretty quickly on this relatively small data set. So rather than 687 peaks, we now have a version of the data set that is summarized with only 3 features, these 3 principal components. We could ask for more or fewer, but we'll take a look at these 3. So you can see I just used the PCA, capitalized PCA method for matter to calculate that. The output of that, this is part of some of our new results classes. So this is a spatial PCA object. The spatial part here just means that it has coordinates, spatial coordinates along with the PCA, and we can plot the PC scores at those coordinates if we want to visualize the PCs as an image. So that's what I'm going to do here. So I'm going to go ahead and use image on my PCA, along with some adaptive smoothing and histogram equalization. So this here is overlaying the first 3 principal components. I can also show you a non-superposed version. So those are the distribution of our 3 top principal components. So principal components are calculated in essentially what we would consider descending order of the amount of variance in the data set they explain. So the first principal component explains as much variation as possible. The next principal component is calculated to be orthogonal to the first and explain the next most amount of variation as it can. And so what it looks like we have here is that we have the first one that is mostly related to kind of the back, the fatty tissue along the back there, the pigs along behind the pig's spinal cord. Our second principal component, 2 here, looks to be mostly in the liver, along with a little bit on the back as well, and a little bit in the brain. And then our third principal component here seems to be a little bit of the spine, the heart, and the liver. We can also see if we superimpose them like that. As part of principal components analysis, we get loadings. So this is kind of the importance of each mass feature contributing to each principal component. Not exactly, because loadings in PCA can be both positive and negative, which makes it a little bit difficult sometimes to interpret these principal component loadings. So PCA can be a useful first way to visualize the data set. So here it's picking up on some of the major structures like the brain and the liver and the heart. So it's useful as a visualization tool. It can also potentially be used as input to machine learning methods as a way to fit machine learning methods that might take too long if we used all of the peaks. In this case, we only have 687 peaks, so that's not too many, but if we had a lot more, then reducing the number of dimensions with PCA might be helpful in fitting a model to the data. So that's PCA. A new method that is introduced in the most recent version of Cardinal 3.6 is one that people have asked for a while now, which is non-negative matrix factorization. This is a method that has been used a lot in mass spec imaging and other mass spectra and spectral domains. So NMF is similar, very similar to PCA in that it's also a dimension reduction technique. The difference between NMF and PCA is in the name that NMF is non-negative. So unlike PCA, where we just saw the loadings can be either positive or negative, which can make it a little bit difficult sometimes to interpret each mass feature's contribution to a particular principal component. With non-negative matrix factorization, the loadings are required to be positive or, well, non-negative technically, which can make it a little bit easier to interpret them and can also make it a little bit more appropriate for non-negative data, which mass spectrometry data inherently is. We can't have a negative abundance, for example. So I can fit NMF using this NMF function. One thing to be aware of with NMF is for NMF, we do have 2 different methods available. ALS stands for alternating least squares. The second method, MULT, is for multiplicative updates. These are two of the common algorithms for calculating non-negative matrix factorization. The default, which is ALS, alternating least squares, that's the default because it tends to be a bit faster and potentially a bit more numerically accurate. The downside to using the ALS algorithm is it can be a little bit unstable when we have highly correlated features. The different features in mass spectrometry can, of course, be correlated, but it's not necessarily going to be enough to cause issues here. If you do have issues with the ALS algorithm, you can just switch to the multiplicative updates one, which is usually going to be a little bit slower, but it is going to be more stable. So if for some reason the first method fails, you can switch to the multiplicative updates one. So you can see that was initialized with PCA, and then we did the updates to find the non-negative matrix factorization. So I asked for, yes. Uh, yes, so the question is on PLS. I assuming you mean PLS-DA or just PLS. So PLS stands for either partial least squares or projection to latent structures. They're two different names for the same kind of method. On their own, they can be used as a regression technique. We can also use them to do classification as PLS-DA, which is partial least squares discriminant analysis. So yes, those are available as well, and are one of the workflows that is covered here. Let me actually get rid of that. So included in the course materials are actually just all of the vignettes for both Cardinal and Cardinal workflows. I'm just going to pull up the bioconductor page for Cardinal workflows here. So what we're working through here is actually just the first vignette for the Cardinal workflows package. This has several workflows for segmentation, classification, and class comparison. We're walking through the first one now on segmentation. We probably will not have time to get through the second and third of these, but the second one here, classification, is what would cover classification using PLS-DA. Actually, this one might not have PLS in it. It does have classification. So let me go back to just Cardinal for a moment. Vignettes. So this one actually, it looks like it does not have PLS in it directly, but the Cardinal vignette for statistical methods does cover PLS. So there is a PLS and OPLS methods as well. Okay, so right now, coming back here to NMF, I asked for 3 components, just like PCA. I asked it to run for 30 iterations. And then here is the result of that. So you can see this comes to us as a spatial NMF structure. So again, it just is a wrapper for the non-negative matrix factorization that bundles it together with our spatial coordinates here. So if you want, by the way, for any of these result objects, these are also a new way of storing results versus the previous versions of Cardinal. So I tried to simplify how the results are stored. So what we have now is a slot for the model data. So this is just the actual underlying model object. So internally, this is an NNMF for our non-negative matrix factorization. And then in addition to that, we also have the position information. So there is a pixel data and a feature data slot for most of these results. So these carry along the same pixel data and feature data that the original data set did that we analyzed. So we can get the feature data and the pixel data. And the names here, these names just correspond to all of the different components of the analysis results. So for this one, for example, we can get the activation. Those are just the loadings. X, which is the scores. And then the rest of these, the next two here, these are just parameters. So let me go ahead now and plot NMF. So here's the overlaid image. Let me also show you each one individually. So these are the individual NMF components plotted as images. So you can see, I think NMF does a slightly better job in this case than PCA did. So the first component here seems to capture the heart along with some of the regions surrounding the heart. The second one here seems to be mostly that kind of fatty back tissue. And then the third component here includes the brain and the liver. And so when I superpose those, I think we get a slightly better visualization of the data set overall than we had with PCA. So let me go back there. Yeah, so I think the PCA in this case is a little bit noisier, and the NMF picks up the heart region a lot better than the PCA did. So NMF, I think, does seem to do a little bit better than PCA sometimes because the data itself is inherently non-negative. So NMF seems to kind of work a little bit better for it because of that. Then we can plot the loadings. So these are the loadings for the non-negative matrix factorization. These are constrained to be non-negative, so they can be a little bit easier to interpret than the principal component loadings. The higher it is, the more that mass feature contributes to the particular NMF component. Simple as that. So for example, looking at this, let me break these out just so I can see them a little bit more clearly. So for example, here we can see that the second component is mostly those lower mass molecules, a little bit of something around 500, but the second component is mostly those lower mass molecules, which looking at it seems to be mostly that kind of fatty back tissue. The third component is kind of spanning the whole range. So we got both low mass, medium mass, and high mass molecules there. So a bit easier to interpret the NMF results there. All right, so let's talk a little bit now about segmentation. So one of the frequent goals of an unsupervised analysis like this is just identifying the different regions of relatively homogeneous chemical composition within our sample. And so one of the ways to do that is with a segmentation, which is essentially just clustering on spatial data or clustering on imaging data. So that's what we can do here with the spatial shrunken centroids method. So spatial shrunken centroids takes in the relevant section here. There's 4 parameters that you need to set for spatial shrunken centroids. The first one is the type of weights to use. Gaussian just uses standard Gaussian weights, so symmetric in every direction for each pixel. You can think of these weights as essentially the kind of smoothing that is done on the resulting segmentation. It's a little bit more complicated than that, but you can think of it as the kind of smoothing. So Gaussian uses simple Gaussian rates, so a symmetric weighting that falls off with further distance from the central pixel. Adaptive weights include adaptation to the local structure. So the adaptive weights will try to preserve edges a bit better than the Gaussian weights. In practice, the Gaussian weights actually do pretty good for this method because we're fitting this to the entire data set, so we have multiple peaks. And so the Gaussian weights are often good enough, but we have both options here that you can try. The next 3 options here, these are the smoothing radius, the maximum number of segments or clusters, and the shrinkage or sparsity parameter. So R is the smoothing radius. So this indicates the area of smoothing. So when comparing each individual mass spectrum to the average mass spectrum for a particular cluster or segment, the smoothing radius here indicates how much smoothing is done in that comparison. So the larger that R is, the more spatial smoothing is going to happen, the more that neighboring pixels will be essentially averaged together. The smaller the smoothing radius, the less the spatial information will play a part. K, this is the maximum number of segments or clusters. So I would often start this as being equal to or slightly more than the number of segments you expect in the result. Empty segments are allowed to be dropped from the analysis. This is an iterative process. So if we end up with some empty segments, those are removed. So you can end up with fewer segments than K here, which is actually often something that we want to happen. Because part of what helps us choose the number of clusters or choose the resulting segmentation. All right, and then lastly, we have S. S is the shrinkage or sparsity parameter. So one of the features of this spatial shrunken centroids method for segmentation is that it performs feature selection as well. So part of the output of this is going to be t-statistics for every feature. And essentially, the higher the t-statistics, the more relevant that particular feature is in distinguishing that cluster or that segment from the others. And part of the way that the method works is by shrinking those t-statistics towards 0 based on this shrinkage parameter. And what that means, practically speaking, is the larger this shrinkage parameter, the fewer peaks will actually be used to determine the segmentation. So if this is 0, that means that there is no shrinkage, there is no sparsity enforced, and all of the peaks will be used in the segmentation. The higher this is, the more of those t-statistics will be forced to 0, and the fewer peaks will actually be used to determine the segmentation. So this is the one of these parameters that we typically want to vary. We typically want to fix R and K and then try a range of different S parameters that get larger and larger, and then kind of see which one seems to give us the best results. So here we're going to apply spatial shrunken centroids. I'm using adaptive weights. R is 2, so that means our smoothing radius is 2. So each pixel will consider up to two neighboring pixels in either direction, in all directions around it. K equals 8, so we're going to start off initializing the segmentation with 8 clusters. And we're going to vary S from 2 up to 64 in powers of 2. There's nothing that says you have to use powers of 2 or any particular pattern here. It was just an easy way for me to choose increasingly higher and higher S's. So let me go ahead and run that over here. The initialization is randomized. So this is a method that is that has some kind of inherent randomness to it. The results are usually going to be pretty similar in the end, but the initialization does matter. So we want to set a seed for the random number generator. That's why I'm using set seed up there. And then I can run this. So in the first step, it's going to calculate the weights and then calculate the global centroid. It's going to initialize the clusters with spatially aware k-means. And then we're going to go through each parameter set and perform the clustering. So you can see it's printing out the number of iterations for each parameter set. And one of the improvements with the current version of Cardinal is that this should run a good bit faster than it used to. We're taking better advantage of warm starts so that if we do pass a sequence of S parameters, each parameter set should be faster than the previous one since it uses the results from the previous iterations. Any questions so far? All right.
Actually, the first error is that I
So the first couple lines at the beginning of the unmarkdown document, you don't need to run those. They're just forbidding the entire document. They're not, you don't need to run them directly. Okay. Yeah. Thank you. All right, so the output from that, because we gave multiple S parameters ranging from 2 up to 64, we get a results list object as our results. So this is just essentially a list that contains the different segmentations here. And it's also printing out a nice little summary for each of those 6 segmentations that we got. So part of this summary, it shows us the parameters that we use, so the R, K, S, and the weights. It also tells us the resulting number of segments. So we started with 8, initialized with 8 clusters. For 4 of those segmentations, it stayed at 8. And then for the last 2, it dropped to 7, and then all the way down to 3. We can see the corresponding sparsity as well. So as we go down across through these different segmentations, we can see that we're increasing S. So we ramped S from 2, 4, 8, 16, 32, and then 64. So as S is getting larger, we're having higher sparsity. Higher sparsity means we're using fewer peaks in the data set to determine the segmentation. So 0.27 means we're using roughly 27% of the t-statistics for peaks are zeros. So 1 minus 0.27, which would be 0.73. So only about 73% of the peaks are being used in that first example. And then in the last segmentation here, sparsity is all the way up to 99%. So we're only using 1% of the 600 or so peaks from the data set. Which is also why, as we get to those higher sparsities, we see fewer clusters in the actual result. As we're using fewer peaks, they can explain fewer regions within the data set. So we drop from 8 down to 7 down to 3. That is to be expected. That is part of how all of this works. And then in addition to that, we have the AIC and BIC. These are measures of goodness of fit. So these are additional values that we can use to help guide which of these segmentations is kind of the best fit to the data and is going to be the most useful to explore further. For AIC and BIC, smaller values are better. Same way that AIC and BIC are used with any other kinds of modeling, linear models, if you've run into these with linear regression and linear modeling. So smaller values of those are going to be better. So we can see that the last 3 models here do seem to be much better than the previous versions. And in particular, I think we're going to focus on the second to last model here. So the segmentation with S equals 32. But first, I'm going to plot 4 of the segmentations. So these are 4 of the most sparse segmentations. Let me jump over here to show that a little bit larger. So here are some of the segmentations for S equals 8, 16, 13, or 32, and 64. So you can see how we start off with more segments. S equals 32 is when we first drop one of those segments. So cluster 8 disappears when we get to 32, when we get to S equals 32. And then going from S equals 32 to S equals 64, at that point, we are using far fewer peaks, and we can actually only support 3 segments in that final segmentation, which we can see is the brain, the liver, and the various internals of the pig fetus. So we're going to take more of a look at S equals 32 here, which we can see includes the brain, the heart, the liver, and some of that fatty back tissue, and just the internal organs. All right, so we're going to focus more on the 5th segmentation here, which is that S equals 32 one, which had the pretty low BIC and the smallest AIC of these. So I'm going to assign that to SSC1 here, pig 206 SSC1. So you can see this returns an object of class spatial shrunken centroids. We have a bunch of different components that we could extract from this model, such as the classes. So these are the actual cluster or segment membership, probability of belonging to the different clusters or segments, along with some other information here, such as the t-statistics. So let's go ahead and plot this specific segmentation. So here we have that specific segmentation, also right here. So we can see segment 7, that appears to be the brain. Segment 5 or 6 appears to be the liver. We have the heart in segment 2 and some of that fatty back tissue in the first segment. When we plot the segmentation like this, what we are actually doing is plotting the segment probabilities. So each of these different segments for clusters from 1 through 7, each pixel has a probability of belonging to one of these. And what we're actually doing is plotting all of the different colors overlaid on top of each other with opacity used to reflect the probability. So that means the areas of solid color have a high probability of belonging to that segment, while areas of a kind of blended color, kind of translucent colors, where you see a lot of color mixing, those are going to be low probability areas where the segmentation is less certain because there's a bit more of a lower probabilities of belonging to any one of these. So that's how you can interpret that you have some areas here that look a bit uncertain because they are a bit uncertain. If we just wanted to plot the cluster memberships just on their own without that probability, we can use type equals class when plotting the image. I'll jump back over here. So the default here is type equals probability. So that's the default that we're plotting there. We can change type equals class, and that just plots the hard cluster membership. Next, we can plot the shrunken centroids, which are similar to the mean spectra, although they're not exactly the same. So these are the shrunken centroids for each of these different segments, which are equivalent to their mean spectra shrunken toward the global mean spectrum based on that S, the shrinkage parameter. I can break out the shrunken centroids for those 3 specific categories. So we have, in that case, the heart, I believe, is the orange. Yeah, the heart is the orange. We have yellow is the liver there. And then the purple over there is our brain. So looking at the mean spectra or the shrunken centroids, we can certainly see some differences. So we see a lot more of those kind of medium mass analytes in the liver segment, for example. But a better way of kind of comparing different segments and seeing which features are the most important is going to be to plot the statistics, the t-statistics. So the way this method works is each mass feature for each segment has a t-statistic calculated based on the difference between the mean spectrum for that particular segment and the global mean spectrum for the entire data set. So these are those t-statistics. So if one of these statistics is positive, that means that particular molecule is more abundant in that segment relative to the mean spectrum of the entire data set. If the t-statistic is negative, that means that particular molecule is less abundant for that particular segment relative to the global mean spectrum, relative to the entire data set. And the way that this method works is by shrinking these t-statistics towards 0 based on that S parameter. so that non-informative features are essentially set to 0 and removed from the algorithm, from the model. So that's why you can see some regions of the mass range here that have no t statistics, because those were shrunken towards 0. Those peaks were not relevant to the actual segmentation, and so their statistics were set to 0, and they're essentially not used to determine the segmentation. So here, let me break out the statistics for those three segments specifically. Let me actually do it like that. It's a little bit easier to see. So 2 here. Actually, let me plot this along with the image so we can go back and forth. So segment 2 here, the orange segment, that's going to be our brain here. Oh, our heart. Thank you. It's getting that point in the afternoon where I'm forgetting what I'm saying. So we have the heart in orange. And the unique thing about the heart is that, well, it is very unique relative to the rest of the data set. So the heart is indicated very specifically by just 1 or 2 molecules, which we can see here. I believe that actually happens to be 153 or something like that. Oops. I meant to do that here. Or not 153, 187. So we have 187 and 186. Those are the 2 peaks that determine the heart. So those 2 ions seem to be the only ones in the data set that are more abundant in the heart than anywhere else in the data set. For the liver, we have the liver in orange. I'll double check that. Yep, liver in orange. So one thing we notice about the liver is that there are way more molecules associated with the liver than these other segments. So we have a lot of molecules, relatively speaking, associated with the liver. Most abundant in the liver appears to be around these ions in the 530 or so range. Then we have the brain, which is the purple segment down here, which seems to be mostly these relatively heavy molecules and also a few of these lighter molecules down here. So that's one of the ways that we can both plot the actual segmentation as well as plot the t-statistics, which are what help us understand what are the different molecules, or at least their mass to charge ratios of the molecules that are distinctive of each of the different segments here. And the last thing I want to show you for this workflow is that we can extract the top features. So these are going to rank all of the features in the data set based on their statistics. So this just returns a data frame. You can see it has more rows than we actually had features because we have distinct statistics for each segment. And so we can subset this ranking of top features to find the most relevant mass features for each individual segment. So for example, here we can look at the heart. We can see it just has only those 2 ions associated with the heart. With the liver, we have 33 molecules from our 600 or so peaks. We have 30 or so of those that are associated with the liver. And then the brain, we have about 20 of our peaks that are important in distinguishing the brain from the rest of the data. Question, yeah.
This, for example, like between like different samples as well. Because this is now based on a segmentation that from 1 tissue.
Yeah, so the question is, can we do the same kind of thing, but with multiple samples or across multiple runs? So it depends on what the actual goal of the analysis is. So if you just want to perform segmentation, so an unsupervised analysis on multiple samples, you can certainly do that just using this same method. And you could, so by default, samples from different runs will not be spatially related to each other. So they may they may end up as belonging to the same segments, but they won't be spatially smoothed with each other. So we can just apply this segmentation method directly to data coming from multiple runs or multiple samples. So that's if we're doing an unsupervised analysis. So we don't have any labels going in, and we don't have a specific hypothesis that we want to test. If what we want to do is statistical testing and test between two different conditions across multiple samples, that requires a little bit of a different approach. So that is something that we will unfortunately not quite have the time to talk about right now. But we have a testing vignette from the Cardinal Workflows package that I'll at least quickly preview here. And then if we have time later, I can come back to this. But so I'm just going to quickly go through this without actually running the code, but to give you an idea of what an approach like this could look like. So this is a data set that we also use this one to show classification, but we also use this for testing. So if we want to compare classes across multiple samples, we can use this workflow. You can follow along with this workflow. So here we're looking at renal cell carcinoma. So here we have kidney tissues in matched pairs across 8 different subjects. These were arranged so we have tumor on the left, we have healthy kidney tissue on the right. So this is the RCC example data set from Cardinal Workflows. So here are the diagnoses. So these are the regions. I selected these myself way back at Purdue. Again, this is more of Livia's data. So we have cancer on the left, normal tissue on the right. Here's just the TIC images from those. And then here I distinguished the diagnoses just using X coordinates, not using the regions I specifically looked at. But to skip ahead to a couple of different ways of performing testing. So one of the simplest ways to perform testing is just to take the mean of all the pixels from each sample. So in this example in particular, we have these eight matched pairs. So we have 8 examples of each condition. So we have 8 cancer tissues, 8 healthy tissues. And so that's the first thing we're doing in this means test call. So I'm passing means test my process data set with the peaks from this data set. I'm passing it what I have here is this rough diagnosis. So this is just splitting up the sides of the slides. I could also just use the diagnosis here, which is the manual region that I selected. And then samples here. So these are going to be the sample IDs. So all pixels that belong to the same sample should have the same sample ID according to this samples argument. So means test, what this does is it will just calculate the mean for each sample and each condition, and then fit a linear model for all of the features, for all the mass features. So we had 54 peaks in this data set from that pre-processing that was filtered down using just some non-specific filtering down from more peaks than that. But we ended up with 54 peaks. So those are those 54 peaks here. The condition is this diagnosis. So that's going to be our fixed effect in the linear model that gets fit for each feature. This statistic is, I believe, is this a chi-square? So this is the statistic from doing a likelihood ratio test using the fitted model for each feature based on this condition. So ultimately, we're going to have the sample size is just going to be based on how many samples we have. We're going to take the mean for each of those samples, fit a linear model, calculate the statistic from the likelihood ratio test, and report the p-values here. As you can see, we just have a couple that are even slightly significant. although these have not been adjusted yet for multiple testing. We can calculate the top features from this. Top features will include an FDR column for false discovery rate that adjusts for FDR. In this case, we didn't actually find any, which brings us to a slightly better approach than just taking the mean. Taking the mean can be fine if you know you are selecting an appropriate region. But the other way that we can do this that we've been using for testing now is using a method called spatial DGMM to perform preprocessing first. So spatial DGMM fits a spatially aware Gaussian mixture model to each feature first. So basically, every ion image is going to be segmented independently of the other ions, of the other ion images. And the purpose for that is to automatically segment each image into the regions that we want to compare. The default setting is to just rank the different segments from this based on their average intensity, and then compare the most intense one. Actually, I think I need to rerun this maybe because this is backwards. So in the current version, these should be ranked in ascending. I guess that's correct there. Maybe this is just a background peak. That would explain why. So these are typically going to be arranged in decreasing order. So the most intense segment is going to be the first one usually. Which
does this segment like the whole issues, or like does it segment it like each other?
So this segmentation, if we are using this as input to statistical testing, each sample here does need to be segmented independently. So we can do that with this groups argument up here. So here we're just passing the same pixel IDs that I would have used a moment ago as the samples in the means test function. So here I'm passing those as groups as the groups argument to spatial DGMM. So that means each sample here is segmented independently. So the segmentation for this one has nothing to do with the segmentation from this one. So each of these are segmented independently. And then they're ranked just so that I can visualize them all together. So rather than having 3 times 8, 24 different clusters here, I'm just plotting their rankings so that it's easy to see which one kind of corresponds to the other in the other samples. So then this would represent kind of the actual data that we would use for comparison down here. So these are the Gaussian components for each of these different segments. So we're going to summarize each segment with its mean. And the benefit of doing this first means that the mean should be more segment specific to individual regions within each sample. So in this case, we want to compare the actual tissue region to the other tissues. So this is just helping automate that rather than manually selecting those, which could potentially cause some bias. And so once we have this spatial DGMM, we can use that as input to the means test function. So we can use spatial DGMM as input to the means test function rather than the whole data set. And then means test will use the segment means rather than the means of the whole sample to do the testing. So the rest of this part is the same. It's still fitting the same kinds of models, just using the segment means instead. And so in this case, when I go to top features and look for if we have any significant ones, using after multiple testing adjustment based on FDR, we do have at least 2 that we find in this case. So these are those 2 where we found a difference. So that's our workflow for statistical testing. And that is an ongoing kind of area of work if we find more PhD students that are interested in working on that, because I think that this approach is much better than this stuff. There wasn't great ways of doing this beforehand. We like this approach because it's relatively easy to use and straightforward. But this is something we would like to further improve in the future if we have PhD students interested in working on this. All right. So any questions so far on anything we've covered up to this point? All right, so in that case, at this point, we have a little over a half hour left. So I'd like to turn things over to Sai for a little bit to talk about some of our kind of current and ongoing future work, to give you a little bit of a preview of some of the stuff we're currently working on. And then when he's done, if there's any time left over, I'm happy to go back over any questions you have, or just try to help you individually if there's anything you would like help with. All right, so I'll turn things over to Sai now.
Okay, so now I will talk about correlation of mass spec images and H&E images. I will try to take as little time as possible. So first, we'll talk about what is correlation. It is essentially just a spatial alignment of two images. So we use registration programs every day in our cameras, on Google Maps with 360-degree view cameras and videos that we find. These types of correlation programs are quite easy to essentially find a solution for, because the subjects of the photos, or like the subjects of say street view maps, they are very rigid and they don't move around.
And
Uh, and
and just to back up one step further, even just to put some context on what we're doing here, and you might already know, but one of the kind of future directions that mass spec imaging is going is multimodal experiments. So incorporating both mass spectrometry imaging along with some other imaging modality, which might be MRI data, might be microscopy data, but other kinds of biomedical imaging. And one of the general challenges of doing that is aligning the images between the two modalities. So we can have, say, microscopy, which has incredible spatial resolution, but doesn't really have a lot of channels, versus MS imaging, which has tons of channels for so many molecules, but not necessarily the highest spatial resolution. And so we can potentially get more out of a data set if we combine these different imaging modalities. And part of the problem of doing that is actually aligning them, which is the problem that Sai is trying to solve here, and will hopefully become part of the Cardinal workflow in the future for users who do want to work with multimodal experiments.
yeah, to extend one of the applications, what we can also do, and what is also being done right now, is essentially transfer of annotations, right? So we have a pathologist working on a H&E image, annotating what is cancer and what is trauma. And let's say we want to do a classification task on mass spec imaging, but we have to transfer those annotations that are done by the pathologist on the H&E image over to MSI, where we can run one of the classification techniques available in Cardinal. So to do that, we have to spatially align those two images first, transfer the annotations, run the classification method, and get our results. So to do that, we need to align the images first. So back to where we are. So image registration, general image registration is quite easy, and it is present uh, in the devices that we use every day. One example is satellite registration, where satellite takes pictures, but satellite also moves. So to combine both of those views or photos taken, a simple affine registration is sufficient. However, for coming back to co-registration with mass spec images and H&E images, where images are multimodal, that brings a whole lot of difficulties for us because one, the camera is not the same. So the actual device that is taking the image is not the same. And the second is the tissue itself, the subject of the photo or the image is also deformable. It also changes. And on top of that, the images that we have also give out additional challenges for co-registration. So one such obstacle is multivariability. Like Kylie said, we have for mass spec image tens of thousands of channels, and for histology image there are just 3 channels. So that is kind of difficult to reconcile for the general image registration programs. One other additional challenge is the multimodality of it. The intensity distributions can be quite different. For histology image, it is quite normalized. We have 0 to 1 or if they are normalized, or 0 to 255, while for MSI images, it can be an arbitrary number depending on how you normalize your MSI images. So this is something else that has to be taken care of when you are doing co-registration. Otherwise, uh, compared to your histology image, your ion image may look very washed out with very low intensity distribution. Another challenge is, of course, different spatial dimensions. Again, like Kylie said, histology image is very, very high in spatial resolution, but has a fewer number of channels, while mass spec image has very low spatial resolution, but it is very rich in channel wise. Again, this is very, very difficult to reconcile for registration programs. Finally, we have information sparsity. This is uh, kind of related to multimodality of it, because we have so many channels for MSI. Information is very sparsely distributed, and this results in noise when you're considering registering. Anyway, so correlation is a problem of multivariate, multimodal optimization, and we want to minimize the dissimilarity of the spatial deformities between the 2 images. So there are some existing methods already for correlation for uh, mass spec images and histology images, but they are not very much suited for these kinds of challenges. We have assisted methods where you need to pick landmarks to do registration. So that is very supervised. And there are some iterative methods that can do unsupervised and automatic co-registrations, but they are very limited. They are not compatible with mass spec data. And there are methods that can do all of these things, but prior training has to be needed, and they will only work for the kind of data that it has been trained on. So to actually solve this problem, we came up with MSI Reg, which is another R package that is free and open source, where it caters to every one of the problems that we had discussed before, including discrepancies in spatial resolution or number of channels, intensity distributions, and all of that, where we have separate pipelines for pre-processing and dimensionality reduction. And once we co-register, we can also do performance analysis of the registration program itself. So this is one of the results for the co-registration program. Here are the pre-processed images of histology and mass spec image. You can already see the differences are quite large. And this is the overlay, mask overlay when we overlay them before registration. And this is the actual overlay of these two images. And after registration, we can be able to overlay the like align the images pretty well. This is possible because we are considering uh, we are addressing every one of the problems that we have discussed before. So uh, noise is being removed here. The number of channels issue is being handled here, as well as aspect ratio problems or where image is present within the frame is being handled in image processing here and here. Anyway, we also have some performance metrics which show that indeed we have improved alignment. They go from global metrics to local metrics as well. In the interest of time, I will try and skip this. But if you have any interest for using this package, you can visit this link or scan this QR code where we have some vignettes for uh, vignettes along with some example data sets that will show you how to co-register mass spec and histology images. And okay, Kylie is not here. All right. Anyway, before Kylie is here, I'll take any questions if you have.
Can you register any type of images that also like multiple images if you have, for example, histology, another method?
Uh,
Modalities.
oh, three more. So I only tested for MALDI, DESI to histology. I am doing some tests for IF data, immunofluorescence. That will probably be very easy, but I haven't done with MRI data. Yeah. Although it shouldn't be too difficult to adapt the current method for that. It is all about getting these representative images. I think for MRI, it is fairly possible and easier to get something like this, but uh, I haven't tested any MRI data with this package yet. With a different. Yeah, I guess so because MALDI data is essentially something where it's analyzed that is being represented as there. I think I guess that is also because we can interpolate any article shape, say triangle or triangle into a square and then just complete the image and the expression. Because even though we do that, we are only doing it to recover the transformation once that is there. You can just apply the transformation to whatever pixel shape that you have and then retain the pixel shape.
So the resolution of all the models needs to be the same, right?
No, it does not need to be. Yeah, so that is one of the problems because spatial dimensions, like I mentioned, is much smaller and that can be like 10 or even 100 times larger. But still we can do the registration, evaluate the transformations, and then do the transformation on a higher or lower or whatever resolution.
What is considered a good score? Like, is it just if we look at the like your opinion, your experience? experience. As long as it after registration is higher, that means that registration was successful, or what is that goals interpreting this forms, because there is no kind of ground.
Exactly. So it is not possible to just look at these two numbers and say that registration was good because, for example, just take these two images, right? So if I were to shrink one of these images to very small shape and then put it over here, the percentage of overlap is 100% because, yeah. So what instead we should do is to actually look at visual images and then look at the numbers and then do a decision, right? So even though it is only showing 95%, the actual amount of overlap is much higher than that because we have a loss of tissue in one of the images here as well as over here. So this is not present in the MSI image, but this part is only present in histology image. So it's kind of just a suggestion, like it has improved the metric, but you really have to look at the images and take the decision. Anyway, so I think I'm done. But if you have any questions or if you would like to know more, there are some vignettes at this link, and you can also email me from GitHub. All right, thank you.